Okay,
Let's start.
I think we should get started.
So, hello everybody. My name is Yoros Kordopatizillos, and I would like to welcome you all on behalf of the co-organizers of this workshop, the Visual Copy Detection Workshop. This is a joint effort between Meta, AI, CTU in Prague, Information Technologies Institute, Google Brain, and Queen Mary University of London. Okay. So let's have a quick overview of what's going on. What is our problem actually? So our problem is simply straightforward. We want to identify the videos, the video pairs that shares visual content. What this actually means is that we need to identify and detect visual copies, video copies. Sorry. So the two main related tasks related to this problem is video copy detection and video copy localization. In the first case of video copy detection, our objective is to identify whether a pair of video is copy or not in a global sense. So let's say that we need a global prediction that tells us whether this is a copy or not. So as you can see here, the first example is a pair of video that they are actually copies. You can see that in the beginning they share content, but the second case, it's a video pair that the two videos are not copies. And regarding the second task, it's the video copy localization. So our goal here is to determine which parts of the videos are the ones that overlap between the two videos. So it's not enough to determine in a global sense, a global prediction. We need to have local predictions for each frame. So as you can see here, with grid border, we can see the overlapping frames, and with red, the ones that are irrelevant to each other. Okay. So some cases where this video copy detection case and where these methods are in use. So the main applications that are useful in general are content moderation, where we need to deduplicate user content and in general to manage what users are seeing and how to process their data. Also for this and misinformation. So the goal here is to identify whether the video source is original or not, and later use it for verification in terms of the veracity or authenticity of a news. And finally, for copyright protection, where we need to attribute the corresponding copyright any copyright material that may be used by third parties. Also, there are several challenges regarding this kind of methods. The first one is scale. So when we go at large scale, we have a very high risk of false positives. This is practically means that most of the video pairs that we will apply the system, they would probably be negatives. And also, in terms of, in a more engineering perspective, we need to process a very large amount of video pairs. So the solutions need to be efficient. Additionally, since the videos maybe have been through significant transformations, the systems need to be robust in novel transformations and be able to quickly adapt when the transformation that is applied in during inference and has not been seen during training, the system needs to be able to find these cases as well. Okay, so very few words about the trends in the literature. So first of all, regarding feature extraction, the main trend is to use pre-trained networks that they are image-based, so they are applied frame by frame and extract global or local representations in order to be used later for similarity calculations. These backbone networks are usually fixed, so this means that we need to be very careful on which task and data the backbone networks have been trained on. Additionally, regarding similarity calculation, the general trend is to generate the frame-to-frame similarity matrices based on the frame representations, and then apply some video similarity network in order to either estimate the global similarity or localize the copied segments and so on. As you can see here, indicative example of a very recently published paper, the Trans-VCL, which was part of AAAI this year. So our motivation here is to build a benchmark initiative where participants will be able to compare against each other with their video copy detection and localization methods. So we run the Video Copy Similarity Challenge 2023, where we will have a closer look actually later. I will present us an overview of the task. And our goal was simply to build a challenging data set and benchmark in order to have a fair comparison between the methods where participants could submit their solution and we needed to apply several restrictions on that. Regarding the results and the description of the challenge, we have a technical report which is online at the moment. You can access it through archive. So if you are interested into more details about that, feel free to have a look. So a very quick view about the program. First, we start with a keynote by Raquel Vasquez Lorente, and then we will continue with Ed that will provide an overview of the video similarity challenge. After the coffee break, we will have the 3 winning solutions presented by the participants, and finally we will have Professor John Colomus to have the final keynote talk. So without further ado, let's begin with the first talk. So give me.
It'll take us a second.
Yeah. Okay.
So
First,
bear
let me introduce you. So we have our special guest today for this keynote. Raquel is a lawyer whose work is related to making audiovisual evidence robust and efficient as a tool for documenting crimes and human rights abuses, and hardening video evidence against manipulation and censorship. Her talk will discuss challenges and opportunities for improving the reliability and authentication of video evidence. It will look at the past, present, and future of using photos and videos for justice and accountability for human rights abuses, and challenge the opportunities that technical solutions related to the authenticity verification and analysis of the visual content brings to those documenting and investigating international crimes. So thank you very much for having you here today with us, Raquel. So the floor is yours. Let me help the presentation. So have this here. Okay.
Yeah, sorry, it's not obvious. The cursor's on the screen.
Okay, and then I just go. Oh,
Yeah, and you can.
okay, fantastic. Yeah, that's good. Okay. Okay. Thank you very much. I'm very pleased to be here today because the challenge involved a video of a dog, and I'm a dog person, so I will never say no to any kind of invite that involves videos with dogs. So where I come from, as Giorgio mentioned, is that I should start by lowering everybody's expectations. I'm not an engineer, I'm not a technical person, I'm a lawyer by training. My background is on international criminal investigations. but I've been working for 15 years with technologies like you, researchers and people developing tools that are being deployed in conflict zones. So I've worked in the Middle East, in Central America, in South Asia, in Eastern Europe, in different capacities, particularly with people who are documenting war crimes, crimes against humanity, and genocide. I've also worked with prosecutors and with people and lawyers defending victims and survivors, and also work on defense. So I have a pretty 360 view of how these technologies can help different parties. I was involved in the early days of what we call now the open source investigations movement. And that's how I started getting into how do we authenticate, how do we deduplicate, how do we cut through the noise of the content that we find online. And I now lead a team at Witness, which is a nonprofit. And our team engages early on with emerging technologies that have the potential to boost or undermine our trust in video. As part of this work, we do proactively engage with technical infrastructures that will set the terms for how human rights video and what voices get lifted or get drowned in the noise. And part of this work has been to engage with deepfakes, developments in authenticity and trust that I know John is going to cover later, and other emerging audiovisual technologies like AI-based production, text-to-video, or augmented reality. So in sum, as an organization, Witness is a global human rights network that helps people use video and technology to protect and defend human rights. And these tools, as we all know, have now become central to the world we live in and the human rights communities we serve. The plan I have for the session is to take you on a journey about the past, present, and future of video for human rights. So I hope you enjoy the journey with me. And I want to very quickly remark, and I will come back to this, why research like copy visual detection, visual copy detection, it's important. And at the heart of it is that with more technology being ubiquitous, where violence is systematic, and video platforms like Meta and TikTok and others acquiring more centrality, footage that is captured in the front lines of human rights defense is going to play an important role in making the world see, care, and bring justice for these human rights abuses. But what will happen if we don't believe what we see? And what if we cannot cut through the noise and filter what may be relevant? And what happens when enforcement of content moderation removes potential evidence? That's some of the questions that I'm going to try to answer today for you, or at least plant some motivation for you guys to continue this research, which I think is going to be key in the world of justice and human rights. And I want to start with a quick turn to the past, because I want to show you how video has played a key role in justice for human rights abuses. And this clip is just really 15 seconds, but it's been so important in the history of justice and human rights.
I think we're not sharing the audio.
Esa es la capacidad de poder responder a las acciones humanas. Eso es lo más importante. El ejército tiene capacidad de reaccionar, porque si yo no puedo controlar el ejército, entonces ¿qué puedo hacer?
It's just this. I know, I mean, it has subtitles, so it's fine. It has subtitles in English, so I think it's fine.
Sorry, I'm just going to make sure we're sharing the Zoom. Perfect.
So, sorry, 10 seconds. We
El valor nuestro está en nuestra capacidad de poder responder a las acciones de mando. Eso es lo más importante. El ejército está en capacidad de reaccionar, porque si yo no puedo controlar al ejército, entonces, ¿qué estoy haciendo aquí?
So this video was key. This was an outtake. Originally, there was a journalist called Pamela Yates in 1982 taking footage and making a documentary in Guatemala during the genocide. And she had a lot of outtakes like you normally have when you're making a film. And then in 2003, she was asked by a Spanish colleague of mine to review the outtakes from an interview she had done with Rios Montt, who is the general that we see here. And my colleague was investigating this case. If we fast forward to 2013, and I want to go back, this was taken in 1982, all this become part of the material that the prosecution presented to prove that General Rios Montt actually had a command and control over the military at the time of the genocide. So he is really confessing in camera that he knew what the army was doing. He knew the army was exterminating in a genocidal campaign the local population, and this was key for building the case against him. Sadly, he passed away before the final conviction, but he was initially convicted, then there was a retrial and he passed away. But this video has been a landmark in international justice. And now we see the evolution, right? Like that was filmed. And now we are seeing videos that are captured by accidental bystanders, by trained human rights defenders who upload it online, and also by perpetrators who may take the video and in some circumstances also upload it to social media platforms. So what we are witnessing in the past 10, 15 years is a big volume of evidential records, right? Like investigators have moved from having limited or manageable amounts of evidence to trying to find the needle in the haystack. For instance, the first trial at the International Criminal Court had 1,400 items of documentary evidence, and that took 6 years of trial. And you can imagine like how much material they are handling now. And if we look at Ukraine today, so I took a screenshot of #Ukraine in TikTok. We have millions of videos from Ukraine, and TikTok is a small size platform compared, for instance, with the monthly users that Facebook will have, which is 3 times bigger than TikTok, right? And if we look at the conflict in Syria, there are more hours recorded of the conflict than the conflict itself has been taking place for. And we also see the velocity of what this material is being uploaded, right? YouTube is still putting up statistics of the content being uploaded by the minute, and the last ones are from 2018, and it was 500 minutes per hour. So I did the math, and that's as far as my mathematical skills go, but you will have to live 82 years to watch all the content uploaded in one day on YouTube and do nothing else, no sleep, no food whatsoever. So 82 years just to watch 24 hours of the content on YouTube. And what we are witnessing as well is that a lot of this content is being taken down by the platforms, by machine-enabled algorithms before it's seen by humans and before it can be preserved for justice and accountability. So I put here 3 examples of YouTube videos that are critical evidence of use of chemical weapons in Syria. There's an organization with a partner and ally of Witness that is called Syrian Archive. Now it's called Mnemonic because it's grown to cover archives in more conflicts. These videos are gone from YouTube. If the Syrian Archive hadn't preserved them, we wouldn't have that critical evidence of the chemical weapons attack in Syria. And another example that I wanted to show you, which was the bottom one on the right, is the first case at the International Criminal Court that inserted content taken from a social media platform. In this case was Facebook. This is a case against Al-Rafali, a commander of a brigade in Libya. And we see content like this being uploaded on a daily basis to Facebook. This is it's a series of videos, it's 7 videos that the prosecution inserted to get the arrest warrant against Rafali. Without those videos, the arrest warrant will have collapsed. So they were critical in getting an arrest warrant against the commander. And now we see with more users coming online, a lot of this content being uploaded. And something important that will tie it up with the talk that John has later is that for these 7 videos, actually they had to present a report by a renowned external institution because there was no provenance data, there was not enough metadata. So we know the violence is the new, the cameras are new. This is a quote from Ta-Nehisi Coates, the North American author, writer, and thinker, to which I will add, what is new is the ability to find an audience. And that is what is key here. And that's why we are here today, of like also to be able to detect that content that floats online, that video. And I hinted, like, when I was speaking about the Werfali case, about the challenges that we find with online video from a justice and accountability perspective. So there are 4 main problems, and those are highlighted actually in the paper and in the challenge, some of them. So the first challenge tends to be that the source is unknown. So it's difficult to understand where the provenance may come from. The second challenge is that the time and place of the footage is not identified or misidentified, right? Like the general miscontextualization that we keep finding across social media platforms. And that's, for instance, why investigators have to deploy geolocation techniques, right? To understand where the actual content was taken from. And other issues that generally happen with video, as you've seen in the challenge, is that video can be edited. And also in this case, I put an example of video being staged, which is, you can find it online. The video is called Syrian Hero Boy. And it was created by a film crew in Malta to raise awareness of like the situation of children in Syria. But it was circulated online without any kind of contextualization, metadata. So people took it for real. Major news outlets circulated around because everything looked pretty real. Every time I show it to an Arabic speaking audience, everybody picks it up very quickly that it's actually a stage, because they say that the voices feel like they are acting, and indeed they are all actors, right? So why this is important is because we are talking here about shallow fakes, which can muddy the waters by casting doubt on urgent and authentic videos, or by misdirecting attention to promoting false narratives. Also, in conflict zones or during civil unrest, addressing these videos can mean the difference between life and death, and it can be the difference between securing justice and enough reasonable doubt to prevent action. So as a quick sideway, this is how the, I'm trying to remove that. Sorry, I'm gonna remove this bar because otherwise you can't see the.
If you move, just if you get to the.
This one.
I can help.
Yeah, I think it's there, it's fine. So it's I can see.
It'll disappear.
Yeah. Should disappear. Okay. So as a quick sideway, that's why like the human rights sector was initially pioneering some of the tools that now we are seeing turn into standards like the C2PA and the initiatives like the Content Authenticity Initiative that John is gonna talk more about. Before joining Witness, I used to work for Eyewitness. I know it's very confusing. We don't have very original names in the NGO sector. So if you are looking for a side hustle, like that would be a great consulting firm. So I used to work for Eyewitness that created one of the first tools for authenticating photo and video. And the status of today, we started in 2015 with the production version, but the beta was in research for a few years. And in the last 6 years, they've received over 45,000 photos and videos that they have been able to authenticate, and they've submitted 37 dossiers and cases to international justice investigators.
Yeah.
Sorry, it's gone. Okay. I've talked a bit about the past, the present, and we have talked about the volume and velocity in which this content is uploaded online and some of the present issues. So looking forward, also what we are going to witness, and for some of you that were yesterday at the media forensics workshop, we were talking about this, which is volatility of information and how generative AI is changing a bit the game with the spread of content and the amplification. So this is a photo that we took online, just people walking on a road. And then we added a tank driving towards the people. And you can see the result at the end. So, you know, because they're quite far away to the naked eye, it will take you probably quite a bit to get through it. So imagine if an investigator has to do this visually and manually through millions of records, right? And we are seeing as well content like this, like using Synthesia and other tools and other platforms that are commercial platforms being used for like purposes that weren't intended to, like creating an entire series of videos to back political campaigns. So we are already seeing that this is having a real impact in situations that where human rights abuses can escalate quickly. And this has been the catalyzer for Witness, my organization, starting to do research back in 2018 across the world of how deepfakes may impact human rights and may undermine the trust in the content that human rights offenders are capturing on the ground. We've been leading a series of consultations. There is a website where we have more detail on reports for all of them. And something that has come really clearly across these consultations, which have been really around the world, right? We've gone to every single continent. I've just come back from Kenya. I'm going to Colombia next month. We're doing Brazil and South Asia before the end of the year. And these are the main concerns that human rights defenders, that community leaders working on at the front lines of mis and disinformation keep pointing out to us, regardless of the country. So I know we are all about the hype of generative AI, and it's important. And as I said, like the commercialization of tools is going to bring more noise and more problems to existing issues. So it's going to amplify them and potentially also create new problems. But shallow fakes and decontextualized videos are still the main cause for mis and disinformation. And the issue that we keep seeing is like how these communities are now overloaded with trying to fact check manually, trying to cut through all that noise and try to debunk every single piece, that increasingly so malicious actors can say, well, it is fake, right? Everything is fake. And that's what we call the liar's dividend, which is a term that Daniel Citron coined. And one of those situations where we see that is this content is creating already a lot of harm is in like political mis and disinformation. We have elections coming up in a number of countries. I know everybody's focused in the US, but there is life beyond the US, and a lot of countries are having elections next year. Hopefully the UK too, but we'll see. And public health disinformation, which was also very prevalent during COVID-19. So, and the corollary of it is that undermining the videos that are being circulated online, those accounts that are trying to put truthful content out, this is creating issues with citizen journalism and evidence of human rights abuses not being believed anymore. And from this, I want to highlight two critical needs that are very directly related to visual copy detection. On our website, we have all the recommendations that we've extracted from working with communities on the ground, but I wanted to highlight these two critical needs because it's where your research comes into play and I think comes alive in the real world, right? And what we keep hearing from communities is that we need more research, development, and deployment of accessible tools, and I want to put the emphasis on accessible. And those tools, tools that can help explain and contextualize shallow fakes, so like just unsophisticated editing or miscontextualization, and including intuitive reverse image and video search, right? And I will go back to this in a second. And the second area is that we need detection tools for synthetic media and generative AI that take into account the needs of those who need it the most, including access to forensic expertise. And I'm going to touch briefly on both of these two, just to bring it really to how communities could use research that you are doing. So most journalists know how to use a reverse image search or a keyframe search for video to see where the first instance of a content has been posted, and to see as well where it pops over time. It is a standard practice, but yet it's not something that is broadly accessible to ordinary people in the platforms that they use it most, right? If TikTok, if you go to the For You page, you won't find it there that in an intuitive way. And Facebook and Twitter don't offer it either on their timelines, right? And neither YouTube, so none of the platforms do so. The most direct match that you have is with Google Lens, which is embedded in Google Images, but it's more oriented towards shopping, right? Not like to confronting mis and disinformation. And as I was talking about as well, one of the key areas is not only access to tools, but access to expertise. And at the end of February this year, we launched a pilot project which connects networks of journalists and fact checkers across the world with people who have the forensic expertise to analyze deepfakes and claims of deepfakes. There is a very important point that came out from running this task force. We have a network of those fact checkers. They send us the cases internally. We check within our team that is not a shallow fake. If we think it may be a deep fake, we escalate it to the around 30 experts that we have. And what happened as we were receiving these cases was that we couldn't escalate many of them because they were actually not deep fakes, and they could have benefited from just having reverse video search more available online. Within like around 15-20 minutes, my team was able to tell that they were, in most situations, miscontextualized or very unsophisticated manipulations. For instance, this one that we received was an alleged toxic cloud caused by a Russian attack in a depleted uranium weapons stockpile in Ukraine from May 2023. It was just most likely a miscontextualized video, but not a deepfake as they were claiming many people to be. And why your research is important is because in the age of generative AI, the necessity for reverse video search is going to become more critical, considering that unreliable at the moment, how unreliable online detection tools are. And this may change moving forward, as we were saying yesterday in the media forensics workshop. But we keep hearing when people turn to these tools, and I showed you before the manipulated photo we did with the tank. We put it through an online detection tool and look at the result, right? Because the photo is real, but that the manipulation of the tank is not, it is still things is not AI generated, right? So also, what do we understand as AI generated? Yeah, I agree, right? Like the photo wasn't originally AI generated, it's been AI manipulated, right? And we've seen with the Pentagon photo that was circulated a few weeks ago that caused the stock markets to tank, how important as well is to have accurate detection on buildings, right? This one is also a photo we created of a White House in flames, and we created a series of them. And it still thinks that the chances are that they are created by a human because the detection tools don't work really well yet on objects. So I think the question here is how we ensure as well that these tools are beyond being accurate, they give results that people can understand, and that they are available, not being necessarily a luxury good, right? because this can have consequences in the real world. I don't know if you've seen this video. I'm not gonna play it because it's long, but it's a video of a general in Myanmar confessing to corruption and receiving bribes. The video is from March 2021. And he was accusing the chief minister. This was an accusation against the government of being corrupt. And immediately people turn online, put it on a lot of detection tools, and it showed that it may be a deep fake. And there was a reason to suspect that it was a deep fake. It was very low quality, it was compressed. There was something off about his behavior that didn't look very natural. The facial expression didn't look very natural. There wasn't a lot of movement. The audio on the lips weren't in sync. So there was enough to be suspicious of, but actually almost certain it was a case of forced confession. But when people put it online on the detection tools, the results were very all over the place, right? So what was interesting about this case was that there was almost no ability among the journalists, the fact checkers, and civil society in Myanmar to have the skills and tools to challenge the deepfake. And there was a real problem when then people tried to do like amateur forensics, right? So this example highlights the problem that there are online tools that claim to show you the reality behind an image or a video, but they may not be accurate, or with they're accurate, the results may be difficult to interpret. And we are seeing other examples, right? Like a similar situation in Gabon, where a suspected deepfake, which probably wasn't, and there were some experts in the media forensic workshop yesterday that I had actually commented on this case. And those suspected deepfakes in a situation like Gabon that already had a politically unstable situation actually was a catalyst for an attempted coup. And the other side of this is when we see that real footage gets dismissed as a deep fake, right? Because now we don't have anymore a way of believing or finding credibility in the information we consume. So from a human rights perspective and justice point of view, why is this important? It's because we have moved in the realm of international justice and accountability from working in environments where it was very difficult to obtain information about the atrocities taking place in a country. I started my career in the prosecution in Cambodia, where actually we had very little visual content. It was mostly minutes and records from meetings, because back then it was impossible to have journalists on the ground. People obviously didn't have smartphones. These are crimes that happened before I was even born. And now we have moved to a situation where smartphones have enabled the capture of photo and video by multiple different actors. And 9 years ago, we thought, this is great. More video, more evidence, more cases, more justice. Wrong. That's the wrong conclusion, wrong assumption, because with ever increasing volume of information comes ever increasing irrelevant information. And we have moved from that world where there was no information to try to find the needle in the haystack. And this can truly burden prosecutors and investigators, particularly when dossiers are directed to national prosecutors that may have the burden to investigate inculpatory and exculpatory information. So you are essentially drowned in material. So I have proven many of these challenges that we have with online content, and also that the fact that to complicate the matter, a lot of this content is being taken down under pressure of legislation, because it may be graphic, it may violate the terms and conditions of the platforms, and then it's not available anymore for preservation and for future cases. So to wrap it up, I wanted to connect how video copy and manipulation detection can meet human rights needs and advance justice and accountability. So the research that you guys are doing, I think it can help in three concrete ways, and Giorgio was pointing at some of those. and I hope they have become obvious throughout the talk. So the first one is that your research can empower digital first responders by enabling tools, as long as those tools match their verification workflows, right? As long as those tools also get embedded into the social media platforms where the content is disseminated. And as I mentioned, shallow fakes are still the more widespread and easier to produce, and the ones that are still causing a lot of issues. The second way in which your research can help catalyze international justice and human rights accountability is by helping investigators, for instance, at the United Nations or the International Criminal Court, triaging and filtering video, right? As I mentioned, like we are now dealing with millions of records for each context. Like there is very few countries in the world where there is no user-generated content that can be probative of international crimes. And visual copy detection can help with deduplication, with identifying near duplicates, with identifying any kind of manipulation. So doing that initial triaging and filtering to assess like at the first layer of relevance for an investigation. And it can also help with vicarious trauma. You can imagine people who are exposed to this content. I used to run a team reviewing visual content of war crimes evidence, and you can imagine being exposed to that content day in and day out have an important toll on the psychological health of people. So any kind of tools that allow filtering, that limit the exposure that an analyst can have to content can really improve the lives of those people who are fighting for justice. And the final point is your research can also help facilitate evidence collection and preservation by helping create a stronger content identifiers for social media platforms. And assess, it goes very connected to the initial assessment of triaging and filtering and how we assess for relevance. So I'm just in time for the first time in my life. I was told 30 minutes on point. So thank you all. That is my email address if you have any questions, or if you are interested in our work as well. We have a microsite now showing some of the policy, legislative, and technical interventions we are working on. Thank you.
Thank you.
Okay. What questions?
Yeah, does anyone have questions for our first speaker? Do you want to take questions?
I can, like a mic, but you know, yeah, like I mean, if anyone has questions, I'm happy. Or like, I don't know if you can see the audience as well. If there is a
Yeah, including on Zoom, feel free to raise a hand or something.
we can see them.
We have one question here.
Yeah, as you mentioned, sometimes if there's something paid,
You know what?
So sometimes if you think something is slow, if you think something deep fake or something like that, it's pretty slow. If you want to pass it to an automatic system, if it's fake or real, then you always have some error capacity. 10%, 5%, even 1%. So we can't actually detect anything 100%. Then if you want to pass it to people, like human fact checkers, it's going to be the example that you mentioned, stock market, it's going to crash. Right? So it's not going to wait for human fact checkers, or even if they check, there is going to be still an effect. So what's the solution? There's no solution.
Sorry, could you, Raquel, please repeat the question for those who are on Zoom?
Yeah, of course. So the question for the audience is whether there's actually a solution or not, because there's always going to be the availability of detection tools, and then at human level, we are still going to be slow because it requires time, right? Like, did I catch it correctly? It was roughly that. So essentially, is there a solution, or are we all lost in the doom of the infocalypse? That's how I took it, right? Yeah, thank you. I think I mean, there are solutions, and I think like the problem is when we try to put all eggs in one basket. Yesterday at the media forensic workshops, it was very focused on technical solutions, which I think they are great, and the ones that we are focusing on this conference, they are technical solutions, right? But and if you go to our website, we have other recommendations that go beyond technical. So for instance, we tend to speak a lot about media literacy and the literacy of the public and have critical thinking skills. I think we need to start talking as well about the literacy of the media. So a lot of like the journalists, the fact checkers, the newsrooms that are not like the BBC, the New York Times, that have a visual investigations team. So those local newsrooms having access to the knowledge and to the tools as well. So they are not circulating unintentionally information that is erroneous or miscontextualized, right? And a lot starts there. So that is another track that we can invest on. Similarly, for instance, from a legislative perspective, we have the EU AI Act that is focusing on like watermarking, labeling, provenance, and authenticity technologies. And we have the EU DSA, the Digital Services Act, that is going to focus on the study of mis and disinformation, right? And how content is spread online, particularly in situations of human rights crisis and conflict. It's also key for us to understand what is the root cause, right? Which I do believe in some of these situations, we still don't fully get how content spreads online. So I think it's a multi-pronged approach. I know it's, and I think it's hard, and that's where like we need to work together. And what I will emphasize is that the responsibilities across the pipeline of information and technology. So it starts with the research and the people developing the foundational models, people commercializing tools that allow for editing, for manipulation, for creating generative text to video, text to image. It's also on the social media platforms, on the major media outlets, and it's also on the legislators, right? And for the legislators, I think the role of these different communities is to try to point out to the real problems and start sussing out like solutions with them. So I'm feeling optimistic today, but like maybe if you ask me the same question tomorrow, I would be like, yeah, let's all pack the bags and I don't know, move to an island with no internet. But like today, I'm feeling optimistic.
Okay, yeah, thank you so much for your talk. That was really great. Yeah. All right. Hi, everyone. Yeah, my name is Ed Pizzi. I'm from Meta AI, and I'm here to present on the 2023 Video Similarity Challenge. So this is the organizing team for our challenge. So Meta AI sponsored the challenge and provided prize money, and it was designed by Meta AI, Czech Technical Institute, and the Information Technologies Institute. We hosted the challenge on the Driven Data platform. So in this talk, I'm going to go over the design of the data set, the design of the challenge itself, the baseline that we provided to participants, and then the results of the challenge. And then later in the workshop, the challenge teams will present their methods. So this was touched on in both Raquel and Yorgos's talks, but I want to just quickly mention one of the motivating use cases to study copy detection in the first place is content moderation. It is one of the key use cases from our perspective. So in copy detection for content moderation, we want to take new media that's being uploaded to a platform, and we want to search and see if this is a copy of any of the images or videos that we have previously moderated. And so this helps us scale content moderation to very large scale use cases, and also makes content moderation more efficient for the moderators. These systems are applied at very large scale, which makes these it's important for them to be very precise and efficient because of the scale at which they're applied. We take many of the design decisions for the challenge are informed by our experience with this use case. So first, I'll just describe the data set. So for a bit of background, the image similarity challenge is an image copy detection challenge we held in 2021 as part of the NeurIPS challenge track. It featured a challenging data set for image copy detection with extensive transforms, including both automated and manually human edited images. And it replicates the needle and haystack setting that we see in applied copy detection settings, where most of the media you're considering do not have any real copies. And so in this data set, only a subset of the images in the data set have any copies. So we create this data set. A key design consideration is we wanted the data set to produce the same metrics consistently for everyone who uses the data set, including across time and the different teams that are using it. So to do this, we wanted to create a data set we could distribute in its entirety, as opposed to a list of URLs, some of which may not be available anymore. So to do this, we start with permissively licensed YFCC 100M videos. This is a data set of images and videos from Flickr. And we take those videos, we blur people contained in those videos. We remove the audio because this is a computer vision challenge. And then we deduplicate the data sets to reduce we deduplicate so there aren't naturally occurring duplicates in the source videos. And we use human annotation to do this so that it's precise. We take short 1-minute sections from the videos that we use to maximize the diversity of the data set, within and limit the data set size. Similarly, we resize the videos that are high resolution so that the data set size is manageable. So then we create copies in the data set. So each data set split is divided into query videos, reference videos, and the majority of videos are in the references so that there's a large database that we're searching. And then we insert copied sections from the references into a subset of the query videos. And this is the needle and haystack setting that was also present in the image similarity challenge, where most queries are distractor queries and don't have any matches in the data set, similar to what we see in applied settings. And this motivates, we will then use metrics that replicates the production challenge of finding all the copies efficiently without false positives for queries that don't have any matches. Then we will apply transformations to the queries so that the queries are more challenging to match. So for the transformed videos in the data set, each video will sample multiple transforms using the Ogly augmentation library. These transforms include frame transforms. So these are image transforms that we apply to video frames, such as geometric transforms, photometric or color transforms, overlays, and then combinations of videos in the visual combination. So stacking videos or blending two videos similar to like a mix-up augmentation. And this also includes temporal transforms. So we, for example, changing the speed of a video. We also model some challenging applied cases using complex transforms. So for example, the overlay onto screenshot transform will embed a video in a template as it might appear on social media. And this mimics the production challenge of matching a video across a screen capture where the video is now in context and that context adds visual content, making it more challenging to match. The rooms transform combines videos in a grid, and this is sort of mimicking what we see from recordings of video conference calls or Zoom sessions and things like that. The last complex transform is called perspective transform and shake. This simulates a phone or other handheld recording of a video that's playing on another screen. And so all of these are inspired by real production matching cases that we find challenging. In the image similarity challenge, we remove a set of challenging negatives, challenging non-copies that are very similar. And typical examples are the same scene at a different angle or the same scene a few seconds apart. In the video case, we instead include some of these challenging negatives. And this reflects difficult applied cases, especially for localization, because the premise in localization is we want to be able to tell where a specific match is and distinguish it from other parts of the video that may be in the same context or location. So we wanted to reflect that here. Some examples of where we see this in practice are different, for example, sporting events at the same stadium or videos by the same creator that were taken in the same room, but are not the same video. So each dataset split includes 500 of these challenging query reference pairs. Okay, so next I will describe the challenge itself. So the challenge took place over 2 tracks. The first track is the descriptor track. So the way this works, this is a video copy detection task, which means that predictions here are pairs of queries and references, and then a confidence score for that prediction. In this challenge, participants would provide descriptors, which would be one 512 dimension descriptor per second. And then a search method was used that it was the same for all participants. So we would, and this is just a simple search using inner product search. This was scored using a micro AP metric or global AP. This is the same metric used in the image similarity challenge. And micro AP works by computing a joint average precision over predictions for all queries. So this is different from mean average precision, where you're computing an average precision per query and then averaging them. Here we're taking all predictions for all queries and then computing one average precision. The second track was the matching track. So this is a video copy localization task. So participants will both identify matching videos and produce localized predictions. So predictions here contain a localization box. This is a start and end time for each video, each of the 2 videos in this prediction. This track was flexible about methods and was not as prescribed as the descriptor track. And we scored this using a generalized micro AP metric, where instead of we use a notion of precision and recall that includes localization, and this was taken from adapted from the VCSL paper. And I will quickly introduce what that metric looks like. So this is a visualization of the metric. I'm going to go over this in very high level detail, or at very high level, because it's a little tricky. But the way this works is we can visualize each prediction and ground truth match as a box in a plane where we have one axis that shows time along the queries and another that shows the database of references we're matching against. So each prediction or ground truth match is a box in this plane. We project predictions and ground truth matches onto each axis. So here we're visualizing the projection onto the x-axis below, and we compute their overlap. Then we sum the lengths of the overlaps, the ground truth matches and the predicted matches, and use these lengths, which are in time units, to compute precision and recall. So precision is the overlap over all predictions, and the recall is the overlap over all ground truth matches. And once we have this notion, and then we do this on each axis, and then the final precision and recall values are the geometric mean of precision and recall on each axis. Once we have this notion of precision and recall, we just evaluate it at every operating point, and then compute an average precision over these precision and recall values. Another rule for the challenge was that participants had to submit code for their solutions, and that code would then run on a validation server that would make make predictions on a subset of the data set queries. And then we would evaluate metrics on that data set subset, and we expect them to approximately reproduce the scores on the full data set. This validation server allows us to constrain compute so that so submissions had to be reasonably efficient. And so we established a compute limit of 10 seconds per query video. And this was all implemented by our challenge platform, Driven Data. So next I'll describe the baseline that we provided to participants. The purpose of the baseline here is essentially to demonstrate what a full submission looks like, including the code submission and solution to each track, and also to provide components that participants could reuse. And we did find that participants did reuse components of our baseline. So our baseline is built on the SSCD descriptor. This is some work by myself and colleagues last year at CVPR. This is a 512 dimension descriptor developed for image copy detection. And we use it here as a frame descriptor. So we'll feed individual video frames through this descriptor and get at 1 frame per second, and then get a vector for every second of video. A challenge of using frame methods in a naive way is that a lot of videos have these mostly empty frames. If we match using SSCD in a naive way, these empty frames match each other at essentially saturated similarity, and which results in low precision. So to resolve this, we explore descriptor normalization strategies. So the first thing we do, so if we match using SSCD naively, the visualization here is precision and recall on the descriptor track. If we match naively, we get this purple line at the bottom, which is barely visible as a precision recall curve because it never achieves high precision. And most of the problem here is these mostly empty frames. If we SSCD incorporates L2 normalization of the descriptor in the network itself. If we modify SSCD to remove that, this already helps a lot. And this is the light blue precision recall curve on the graph. And the reason this helps is that these empty frames are very low salience. And if we remove L2 normalization, they have a low descriptor norm, which means that they now match at low confidence because the inner product search, they have low inner product. And that is sufficient to make this problem much better. But we also experiment with score normalization. This is a technique we use in the image similarity challenge. The idea behind score normalization is we want to downweight the similarity for query vectors that just match a lot of things. And the match to the reference is not very specific. And perhaps it matches vectors in a background data set just as well And so it's more likely to be spurious. So we implement this by adjusting the similarity, by subtracting some constant times the similarity of a query vector to its nth nearest neighbor on a background data set. And so to implement that here, we just use the training set as the background data set, and then apply a score normalization correction. Our best results add L2 normalization back and do score normalization. To make localized predictions for the matching track, we use temporal network localization. So this works first we compute a frame similarity matrix for 2 videos. So we take a pair of videos that we retrieved from vector search. Then we have the pair. We multiply their descriptor matrices, and this gives us a notion of similarity between all video frames of one video and all video frames of the other video. And what we are looking for is, true temporally consistent matches have this diagonal line pattern, where as we advance time in each video, there's this local maximum of similarity, as we see here. We give the similarity matrix to a temporal network, which infers a graph problem from the similarity matrix, and then looks for essentially a long path of high similarity in that similarity matrix. And this is a temporal network prediction in blue here for the similarity matrix. With that, I will discuss results of the challenge. So we had more participation for the descriptor track, where 48 teams made submissions, of which 10 teams qualified for phase 2 by making full code submissions. And of those, 5 outperformed the baseline in the second phase of the challenge. For the matching track, 18 teams made submissions. Of those, 5 qualified for phase 2, and 4 outperformed the baseline. This is what the leaderboard looked like for both tracks at the end of the competition. So just a few observations here. First, we had the same 3 teams placed in each of the competition tracks in the same order. In general, teams that did well on the matching track also had good descriptor track performance, and was mostly a subset of those that competed on the descriptor track. In the lower left, we have the same leaderboard, but translated into team names as opposed to what are sort of driven data usernames. One other observation is that almost all teams that compete in both tracks have higher scores on the descriptor track. And this is essentially because the matching track is more challenging. The metric now incorporates localization. And the one exception to this pattern is the first place team, WeChat CV, where they outperform on the matching track, suggesting very precise localization. So to discuss the validation step, all teams code reproduce well on a data subset. So we were happy with how the reproduction worked from the code submissions. And also in the second phase of the challenge, all of the submissions were within time limits. We did rule that some submissions were ineligible for the challenge, but we did not exclude any teams because teams could make more than one submission. And this came down to the method of edit detection. We decided that edit detection using frame data was within the rules of the challenge, but that using video metadata to detect edits was not in the spirit of a computer vision challenge. But we regret that this wasn't clear to all the participants. Because both of our tracks use metrics that are based on average precision, we can visualize the different operating points in a precision recall curve. And so this is what that looks like for the top 3 teams on both tracks. On the descriptor track to the left, we see a little bit, we see different amounts of trading off recall for high precision. And so among the top 3 teams, the teams that have the most precision in the higher precision operating points have less total recall in the lowest precision operating points. In the matching track, we see that the first place team has a significant advantage across operating points. So we perform a few analyses of the results to evaluate what makes things more difficult or easier to match. So the first thing we consider is the number of transforms applied to a query. So we do this by creating a data subset. So we're just taking the existing predictions and then filtering them down to queries that contain a certain number of transforms plus all of the distractor queries. As we do this, we find in a general pattern of as we add more transforms, the more challenging a video is to match, as we would expect. One exception to this is on the descriptor track. We see that the first place team, WeChat CV, becomes more accurate as we go from 2 transforms to 3 and 4, which may be explained by their edit detection is more accurate as we as videos are more obviously transformed by sampling more transforms. Then we consider the specific transforms to see what makes videos most difficult to match on this data set. So here we're taking an average metrics across the top 3 teams, and we find a general pattern that transforms that mix video frames, so either a spatial mix or point-wise, such as the rooms transform that combines multiple videos in a grid, or the blending 2 videos as in a mix-up kind of transfer. These are the most challenging for our challenge participants. And the easiest transforms are temporal transforms. And this is essentially because all of the participants use frame-based descriptors, as did our baseline, which are not affected very much by temporal transforms. One last thing we consider is the effect of the challenging negatives that are evaluated from that we found using human annotation in the dataset deduplication step. So these were the challenging negatives that we added here in the video similarity, but we were missing in the image similarity challenge. And as we evaluate with and without these challenging negatives, we essentially find without the challenging negatives, all solutions improve somewhat, although the first place team is not affected very much by this. On the descriptor track, we find that the differences are fairly large relative to the gap between teams, as the descriptor track was, team performance was more similar in general. On the localization, on the matching track, we find that the differences are not that significant. And I should say on the descriptor track, these gaps are significant enough to make the second place team, friendship first, competition second, overtake the first place team. So last, I'll just conclude with a couple of observations from running the challenge. So first, we found that there was more focus on descriptor improvements in general in this challenge. We saw this both in that there was more interest in the descriptor track, first of all, and then, but even on the matching track, we found a lot of focus on improved descriptors for both copy detection and for localization. And in fact, 2 of the finalist teams used similar localization of the baseline. And this was surprising to us at the outset because we believe that our localization for the baseline was one of the weaknesses of the baseline. Yet 2 teams got it to work quite well. And the first place team is somewhat of an outlier in their focus on localization methods. Another pattern we saw is that all teams use frame-based descriptors as opposed to models that compute features over multiple frames together, such as native video models like ResNext 3D or slope fast networks and things like this. This is not too much of a surprise given the literature, and we do see some combinations of frame level descriptors. But this was something that was common to all of the winning teams as well as our baseline. One last note is that it's difficult to isolate in the context of a challenge the task of copy detection from edit detection. And part of the reason for this is that the source data sets that we have available to us that we can use to create these challenges, such as YFCC 100M, which has a photography bias, are unusually unedited compared to videos you would see if you went on social media or television or just any other kind of source of video that we usually come across. And so what this means is that in practical applications, edit detection, that something is edited is not necessarily a signal that it has been, that it is a copy. These are kind of orthogonal problems, and this is just something that we know. Our intent here was to study copy detection because there are other data sets for edit detection. That said, we could have made edit detection less attractive for this challenge through our design decisions. So in particular, we could have inserted distractor clips into distractor queries so that they all appeared to be edited in this way, or to be a combination of videos. We also could have transformed all queries consistently, whereas some queries were not transformed in this data set. So to summarize, we introduced a challenge and data set for video copy detection and video copy localization. We designed the data set for stable metrics across time. The participants in this challenge improved descriptors and localization methods and significantly improved on the baseline. Our technical report on the challenge is now available. You can find it on arXiv, or you can go to the workshop website. And the data set remains available through Driven Data through their open arena for this challenge. So our thanks to everyone who participated in the challenge, and I look forward to everyone's participant talks. And that's it. Are there any questions on this?
Really quick question on the micro AP. Just really, why are we not doing MAP? Why is it micro AP? Just something about the setup of the challenge, or because I mean.
Yeah. Okay. This is a great question. I'll just repeat it for Zoom. The question is basically why micro AP? Why not mean average precision? I mean, one of the things is something that is important in both this challenge and the image similarity challenge. Most of the queries don't have any matches, and so the mean average precision is sort of like undefined in that case for the queries that don't have matches. And part of some of what we're trying to model is the difficulty at scale, where you have to like really efficiently, any copy that you can't find really efficiently, you won't be able to find at enormous scale, because now if you hit this like wall where you have to retrieve way too much stuff and consider. So in the context of a small data set, we can't directly model large scale retrieval, but what we can do is score, use a metric that, like one of the problems is calibration. So even if you have perfect micro EP, if you have perfect MAP, if some of the copies have really large like distances, like descriptor distances, and then other copies, other non-copies of small distances, these aren't calibrated, and you can't set a threshold for production retrieval that will separate your copies and non-copies. So this is something we wanted to like model here. But yes, this also makes the distractor queries more challenging, because our metric now, the results for them have to be beyond most of the copies to get high precision. Did you follow that answer? It was a
Yeah,
little long.
we can, like, discuss it a bit more afterwards, just-
Okay, yeah. It's a very good question. Yeah. Yeah, great, thank you.
So for the challenge, we get a few, you could say in the copy or edit. But in practice, if you, let's say, have a system that don't then copy on, whatever, then what do you actually, how do you define edit versus copy? What is the procedure there? What do you consider?
Yeah, so this, basically for this challenge, we're just trying to find copies. But in creating the data set, we edited the videos to create copies. The interesting case here are partial copies where the whole video doesn't match, like it's not an exact copy of the video, only part of the video matches. And to create copies of that kind, we insert parts of a reference into the query. So there is this edit, and then participants then can detect edits and then get an advantage in their copy detection. So we don't define a notion of edits. But it is something that that participants can make use of and in practice do. Yeah, does that answer your question?
People to see what they consider as copy, what they consider as edit in practice.
Oh, I see. Yeah, I mean, so the notion of copy differs based on the use case, like the specific application. Yeah, so it can differ. I mean, for example, if you're trying to detect misinformation, like the caption might be really important. But if you're trying to detect, depending on what you're trying to match, you may want to match across, the addition of text. So yeah, there's a little bit of use case specific definitions. Yeah. All right. Any other questions? If not, we can break for our coffee break.
Thank you.
All right, thank you, everyone.
Thank you.
Thanks.
I'm running because I'm late. Okay.
Yeah.
Oh, the copy. Take off the photos, actually. So, yeah, maybe, yeah, if not, I'm out.
I'm just putting the slide up that has our schedule, so that anyone joining Zoom can tell what we're doing. All right, and then I'll remove this. All right.
Hey, how's it going?
How's it going?
Hey, by the way, I'm a user of SSCD, so
That's
I'm very
great.
cool
Oh,
too.
that's awesome. Yeah.
But we're using it for a weird reason. So
Okay.
I thought I'd share with you
Yeah.
what we're doing and tell you a bit about it. So I work for Samsung,
Yeah.
and we are, we have a lot of these real world situations.
So you mean like the detection is possible?
Sorry, I was gonna try to just.
Yeah,
mute while we're-
yeah, good idea.
There we go.
Yes, it's finding that you don't have to trust.
Right. So, I have a little back on the lights and have like this piece of stuff on this and stored in there. Is it really decentralized in the way that perhaps that's quite required? My person into accessing services. So, yeah, that's a challenge.
Yes,
All right, everyone. I think we're going to get started with the participant presentations. So the way, actually, before we get started, Is Jinhua here?
I'm Bevan Ma. I represent our teams to answer audience questions.
Oh, great. Okay, great. All right, perfect. You're on team WeChat CV.
Yes.
All right, great. Okay, great. We're gonna start with the first place team's presentation, and then Feipeng Ma is here to answer questions afterward.
Good morning, everyone. We are members of the WeChat CV. We are delighted to be here today to share our winning solutions for the competition in 2 tracks. Our solution in descriptor track named a dual-level detection method for video copy detection. At the beginning of the competition, we conducted a detailed analysis of the data and identified 3 typical types of videos in the query set. Additionally, we discovered the challenges associated with each of them. The 3 typical types of videos are as follows: unedited videos, copied videos with general editing operations, and copied videos with multiple scenes in each frame. Unedited videos refer to query videos that have not undergone any editing operations. These videos are not copied, but they may retrieve very similar videos from the reference set, leading to negative false matches. Addressing this scenario is challenging, particularly from a feature extraction perspective. Copied videos with general editing operations present challenges for representation. We require a feature extraction model that can handle various hard augmentations in such scenarios. The presence of multiple scenes within video frames makes it more challenging to obtain a strong representation. The extracted features need to possess invariance under different augmentations and be capable of simultaneously matching multiple scenes in reference set. To address these issues and challenges, we propose a dual-level detection approach. This figure shows our framework. Our framework consists of 3 modules, including video editing detection module, frame scenes detection module, and a basic model to extract frame-level features. For unedited video, we directly use a random vector with small norm and negative bias term. For video with general editing, we extract features of each frame by our pre-trained basic model as descriptors. For video with multiple scenes, we detect and split the scenes in each frame, then use basic model to generate descriptors. In the following, we will introduce each module in detail. We use contrastive learning on the VSC training data in frame level. As shown in below, our network structure and loss function are borrowed from SSCD. The difference is that we trained not only the CNN-based backbone, but also the VIT-based backbone. In addition, we use more stronger augmentations. In this slide, we show the various augmentations that are adopted in our training. In addition to general augmentations such as flipping, rotating, cropping, adding noise, scaling, etc., we also use adding text or emoji on the image, mix-up, etc. We use video editing detection module to detect unedited videos. The motivation behind designing the video editing detection module are 2 points. Firstly, it aims to filter out unedited videos, ensuring that only relevant and edited videos are considered during the retrieval process. Secondly, the module helps reduce computational costs during retrieval by excluding unedited videos, thereby optimizing the overall efficiency of the system. Additionally, we discovered that data augmentation follows recognizable patterns. Therefore, we can implement this module using a simple network architecture. As shown in the figure, we adopt clip to extract spatial features for each frame and Roberta to learn the temporal relations between frames. Finally, we use the class token to perform a binary classification task. We train the module on the query videos of training set and use cross-entropy loss. In this slide, we present the performance of this module. As mentioned earlier, Data augmentation is a recognizable pattern, which enables our model to converge quickly with high accuracy. We also showcase the score distribution on test query videos, where the majority of samples are concentrated in the score range of 0 to 0.001 and 0.9 to 1. By using a small threshold, we can effectively filter out the majority of unedited videos. For copied videos with multiple scenes in each frame, we design a frame scenes detection module to deal with them. We think it is difficult to capture the different details with a single representation for frames that have multiple different scenes and strong augmentations. And, as shown in the left figure, scenes are usually concatenated along one side and one frame usually has an even number of scenes. Most of them have 2 or 4 scenes, so we can use traditional image processing methods to detect and segment the scene in the frames. The right figure shows the processing details. Based on score normalization, we modify the integrated bias to suppress the score of unedited videos, which corresponds to a re-ranking of the retrieved results. We modify the bias term. When the predicted score of video editing detection module is smaller than 0.001, which means the query video is unedited, we replace the bias term with -100. The results on the leaderboard demonstrate the effectiveness of our approach. And we sample 20% query videos from training set as validation set to perform ablation study. Our ablation study demonstrates that each module delivers significant improvements. From this slide, we present our solution on the matching track, named a similarity alignment model for video copy segment matching. The framework is shown in this slide. We first follow the methods on descriptor track to extract descriptors for videos and find the query reference video pairs. Then, we propose a sequence matching method to generate similarity matrix for query reference video pairs. After obtaining the similarity map, we will process the similarity map. We use a classification model to recognize negative recalls and use similarity alignment model to output noiseless matching score matrix. Finally, we can get the target output with post-processing. For the embedding model, we use the basic model on descriptor track to extract frame-level features. It is important to note that we didn't use video editing detection module to filter out unedited videos and did not use score filter normalization. Then, we follow the retrieval process in the descriptor track to get the candidate query reference video pairs. Here, we present our method for generating similarity maps. Due to the utilization of the frame scenes detection module, the length of some videos may become an even multiple of the original length. Therefore, we designed a frame sequence matching approach. As shown in the figure, firstly, we split the videos into sub-image sequences and we got a long frame sequence. Secondly, we use this long sequence to retrieval the most similar reference videos. Then, we calculate the similarity between each sub-image sequence and the retrieved reference video. We retain the sub-image sequence with the highest similarity and then compute the similarity map with the reference video. For videos with multiple scenes within frames, the entire process, including all steps, is applied. For other videos, the process includes only steps 2 and 4. After obtaining the similarity maps, we first process the similarity maps. We train 2 models to process the similarity map, one for detecting if the similarity map contains copied segments and another for reducing noise in the similarity map. As shown in figure, we utilize MobileNet v3 for classifying whether the similarity map contains copied segments or not, and our model can discard 95% of the recalled samples with no performance drop. Through this way, we can remove most of false negative samples and increase efficiency. For denoising, we use high-resolution net to process similarity map. To make the input and output sizes the same, we set the stride of the first 2 convolutional layers to 1. At the same time, the target changes to the heat map generated by annotation. The final score is obtained by the denoising similarity map. We show the classification results of different threshold on our validation set. When using 0.5 as the threshold, the precision and recall of the similarity maps without matching segments are both 1. But our target is similarity maps with matching segments, so we choose the highest scoring 10,000 matching samples to ensure a high recall for similarity maps with matching segments. In this slide, we present some visualization results. We can see that the similarity map without copy segments is easily identified after denoising, and the continuous line segments in the similarity map after high-resolution net are very obvious. After obtaining a matching relationship matrix, the post-processing is required before submitting the final result. The post-processing including 1. Using a filter threshold to remove false positive matches. 2. Identifying multiple detections with the connected components algorithm. 3. Detecting the matching relation with RANSAC regression. In this slide, we show the whole process of denoising and post-processing. The matching segments of the similarity map become very clear after denoising, and multiple segments are more easily identified after the connected component algorithm. And finally, we use the RANSAC algorithm to obtain the specific locations of these segments. Our ensemble approach can lead to significant improvements. Score is the matched score list for points, which is first filtered by score threshold T, then filtered by RANSAC regression inner points. We use the mean score and penalize the score variance, where alpha is the weight of penalty. Also, we penalize those matching segments that are not diagonal. Our model finally uses 3 sets of hyperparameters T and alpha. In the figure, we show the precision and recall of high threshold and low threshold. We can observe that the result of high threshold, the red line, can keep a high precision when the recall is low, but drop quickly when the recall is high. And the result of low threshold, the blue line, can maintain an acceptable effect when the recall is high. The green line demonstrates that our ensemble approach can combine the advantages of both results. Our performance on the leaderboard far surpassed that of other teams, demonstrating the effectiveness of our method. Additionally, the minimal performance degradation observed when switching to a different test set showcases the strong generalization ability of our approach. Thank you all for listening.
All right, thanks to Team WeChat CV for presenting their method. And we have, just hang on one second and I will, and then we can take some questions. Does anyone have questions for this team?
I have a question.
All right.
Hi.
Hello?
Thanks. Yeah, hi. I have a question. Well, first of all, congratulations on winning.
You know what, John, do you want to come here? Because I think actually we may not be able to hear.
Oh. Hi, sorry, I say it again. Yeah, first of all, congratulations on winning. I have a question. It's just specifically about the performance gain you got using a VIT backbone versus like a CNN on the, the basic descriptor. I mean, you have a lot of other kind of engineered things to go higher after that, but that specific ablation, I don't know if you did it. I'm interested to know how much that gave you.
Sorry, I don't hear clearly about the question.
Okay, the question is, how much performance gain did you get using VIT as a backbone instead of the CNN backbone? Just that specific ablation.
I understand. In our practice, we use CNN-based backbone at first, but after we choose, after we are at the end of the computation, we change the backbone to VIT based, and we use the stream format of VIT. Of the original VIT, and we find that the VIT is the can get a better result. About about 2 points.
2 percentage points. Okay.
Maybe 1 or 2. I don't remember very clear. Sorry.
Okay, that's great. Well, thanks for the answer. Okay.
Any other questions? I actually realized.
Hello, I have a question.
Yeah,
Hi,
go ahead.
Suzy.
Yeah, go ahead.
Hi, Pace. Hi, Satan. For the contributed to your great. And second, I have a question. So, in the matching track, you have proposed a very interesting matching algorithm to match the acquisition. So, how can you think out about this method? Is it inspired from other works, or you think of it totally on your own? It is very hard to think from my perspective. I think about it for 2 weeks or 3 weeks, but I haven't think of anything. The only thing I think of is to tune the parameters of the temporal network. So it is very interesting to see your team have done this one and complete with it. Could you give me some inspirations about how you classical about this method? Thank you.
Okay, a very funny question. In the beginning of the computation, we use VCR and we reproduce the results of these methods, which is published in July 2023. And based on this method, we find that it's difficult to continue improve the performance. And we think that maybe we should do some make more tries on the simulating map, and we use the as described in our video. Simulated map processing methods like denoising and filtering. So we finally choose this method.
Okay, congratulations again.
Okay, thank you.
All right. Are there any failure cases for the denoising method that you noticed?
I can hear very clear. Can you
I'll try
again?
Yeah, I'll try again. Are there any failure cases you noticed from the denoising method?
The denoising method?
Yeah, this on the similarity matrix.
Sorry, I can understand your question.
The question was whether any failure cases when you applied denoising method on the similarity matrix when you.
I understand. That's a type of that. In fact, we first filter out the failure simulated map, and then we denoising the rest simulated maps. And as for you, the pin map is so the rest simulated maps are most have matching segments.
Okay. Well, thank you very much for the presentation. And yeah, a round of applause for Team WeChat CV.
Thank you.
All right, so next. All right, give me 1 second. Okay, next we will hear from team friendship first, competition second. Yeah, I will play that. Let me share my screen again. Okay, here we go.
Hello everybody. Today we will talk about feature compatible progressive learning for video copy detection. We are Wenhao Wang from Rigor University of Technology, Sydney, Yifan Sun from Baidu Company, Yiyang from Zhejiang University. The competition is held by Meta AI in CVPR 2023. First, I will introduce the background. That is our second place solutions to the Meta AI Video Similarity Challenge. That is VIC 22 in CVPR 2023. In the mapping tracks, it requires that competitors use the models to identify specific clips from query to the reference videos. And in the descriptor track, competitors are required to use a 512 dimensional vector to represent a video, and then the representation vectors are used to match it. Our solutions are inspired from the IIC21 winning solutions, the FOSO and the CNNCL. FOSO is a feature-compatible self-supervised learning for large-scale image similarity detection. And the CNNCL is contrastive learning with large memory bank and negative embedding subtraction for accurate copy detection. These two works are for the image copy detection, and we are focused on the video copy detection. We think that there is no gap between video copy detection and the image copy detection. The image copy detection can be used directly to the video copy detection. Our feature-compatible progressive learning are built on our previous work, the BOT and D12V and ASIL. The BOT and the D12V is our winning solutions in IIC21, and the ASIL is a research paper on image copy detection that is published on the CVPR 2023. Okay. Our progressive learnings can be divided into 3 stages. First, the base training stage. Firstly, we generate the edit copies, that is, given an original image from the IIC21 dataset. The original images are transferred into the edited copy. We design about 20 plus transformations to transfer the original image. For example, we randomly pick 3 transformations from the 20 transformations and then insert it on the original image. Then we can get an edited copy. We repeat this progress for several times, and then we have many edited copies for one original image. We denote one original image and its edited copy as a class. Then we have the class concept. So we can perform the matrix learning on the generated class. There are 1 million image, training image in the AAC21. We pick about 100,000 training images from 1 million image to train a model. We use the cosine phase loss as the supervision, and the backbone for the base training state is CodeNet. The CodeNet is used to extract the features. Okay, that is our base training state. Then we go to the feature compatible learning state. The base network is trained and fixed, and it is only used to extract the features of the original image. And then we train N new networks. And each network is used to extract the feature of original image. We use the error distance to regularize the distance between the original feature get from the base network and the new network. You can see that the L compatible equals to the sum of the distance between two features. And final loss equals to the matrix learning loss, that is the cosine phase loss, plus the compatible learning loss. That is the training loss in that state. We use 6 backbones for the new network. That is the ResNet50, ResNet50, SKNet50, weighting transformer, swing transformer, and T2T VIT. After the training, we can visualize the training the feature. You can see that with the compatible learning, the feature of the edited copies and original images are near. However, if we don't use the compatible learning, the features getting from different models are far away, and therefore they cannot be seen and ensemble in the feature level. So with the feature compatible learning, we can ensemble the query features and the reference features. We simply use the average of the features as the final features. Note that we don't use the median position as in the fossil paper. We simply find that the median position is not work in our pipeline, so we just use the mean as the final results. The feature compatible learning enables the ensemble on the feature level. Is very useful in the descriptor track. Then we fine-tune our dual models on the ground truth pairs. The ground truth pairs are generated from the labeled training videos. Given the videos, we first transfer it to the several image pairs. That is because we can get the labeled clip from the original videos, and then we sample the image from the videos, so we can get the positive image pairs. Simply, we have the negative image pairs. Then for each novel models, we pull code the feature of image in its positive pairs and push away the features in its negative pairs. You can see the positive pairs is getting by the error distance from two novel network, and the negative pair is getting, or is also getting from the error distance from a positive one and a negative one. Then our final loss equals to the L matrix, that is the cosine phase, and the L computable ring that is introduced before. And L positive minus the L negative. That is our final training state. In conclusion, we have three training states. First, base training. Second, the feature compatible learning. And last, the phase fine-tuning on the ground truth pairs. That is our feature compatible progressive learning pipeline. Okay, finally, we can get some visualization. You can see the largest similarity equals to 0.55. The two images seems very similar without any difference. And when the similarity become a little smaller, that is 0.45, the two images have some difference. And in the similarity equals to 0.35, there is a bigger difference. And if the similarity is lower than 0, the difference is very bigger, especially on the similarity equal to minus 0.25. The two images are very different. We get the match in the image level, and then we transfer the image level match to the video level match. That is very easy. We can try to get the maximum similarity between two videos. Okay, that is the visualization. Finally, we compare our method with other competitors. We get the second place in both matching track and the descriptor track. In the matching track, the first team do something more, design a complicated matching method to match the query clip from the reference clip. However, the retrace uses the temporal network given by the baseline method. And we use this one to matching the features getting from the descriptor track directly. So our performance is a little low than the first one, but we are very better compared to the baseline method and the third place method. In the descriptor track, we also use some tricks. For example, we use the Euro V5 to detect the overlay transformation in each video. And we also design models to drive the video, whether a video contains the transformation. So the performance of ours is similar with the top team do something. We got the 85.14 and the top team gets the 87.17 and the baseline gets the 60.47. We can find that in both tracks we improve the baseline significantly. That is the results of matching track and the descriptor tracks. That is our feature completable progressive learning for video copy text. Thanks for your listening.
All right, thank you for the presentation from our second place team. And yeah. Okay, and then okay, does anyone have any questions?
Oh, I have a question. I have a question.
Okay.
Can you hear me? I'm just
Yes.
curious,
Okay.
how much improvement does it have to use future compatible learning compared to like other traditional methods like concat and dimension reduction? And did you conduct an ablation study about that? How much improvement, yeah, does
Okay,
it
okay,
have?
I understand that.
Okay.
Okay, thank you for the questions. Firstly, I found that using vision transformer isn't very suitable for the video copy detection task. So if I train the vision transformer directly, I cannot gain a perfect result. It is very bad. It is worse than the CN at last night. So you mean I need to concat the feature of vision transformer and the CN then to reduce the dimension. I think I have tried it, but it is much lower than the only use the CN. So when training the VIT backbone, I use the feature compatible learning. So with the feature compatible learning, the performance of VIT is 2 points better than the CN. So up to example, the final result is about 3 to 4 points better than the original coordinate. Okay, thank you.
Okay, I see. Thank you.
I had a similar question. Are there any patterns you notice between what types of copies the VIT performs better than the CNN at?
The question is that you mean which patterns is much better from VIT than the CNN, or what is the question?
Yeah, just any patterns you notice about where it outperforms the CNN.
The pattern you mean is the transformation?
Sure, yeah, anything that you've noticed.
Okay. In fact, I don't check this one. You let me check it by myself. I have raised the trained models. Thank you.
That's fair enough. Any other questions for our second place team? Okay, well, thank you again for the presentation. Yeah, so just a note on schedule, we're running about 15 minutes behind. As long as that works for everyone, the next event in here isn't until 1:30, so we have the room for a little bit. All right. Okay, so next, our third presentation will be from Line CVL, and this is this video is by Peifeng Zhu.
Hello everyone, I'm Peifeng Zhu from Line Corporation.
Wait,
Oops, hang on.
Could you share the screen?
Yeah, hang on. I hit something wrong. All right. Okay, here goes.
Hello everyone, I'm Peifei Zhu from Line Corporation. I will present our third place solution to Meta AI Video Similarity Challenge. Let me start with the overview. Here we proposed a simple yet powerful video copy detection pipeline, which is shown in this figure. We have query videos and reference videos as our inputs. Since we find frame-level filter is more powerful to detect and localize copied segments, we extract frames from the videos first. Then for query videos, because they can either be original videos or manipulated videos, we build a model that can predict whether the videos are manipulated and what type of manipulations they have. Then we choose DTA, test time augmentation, according to the type of manipulations they have. On the other hand, reference videos do not contain any manipulations, so these two steps are skipped. Then we extract frame filters using an ISC-DT1 model and apply post-processing, which includes consistency weighting and temporal concatenation. The generated embeddings are submitted to the descriptor chalk. For matching chalk, we use a temporal network method to localize the start and end of the copied segments. I will talk about more details of each part. First, for filter extraction, we use an ISC-DT1 model, which is the first place model of ISC 2021 descriptor chalk. It has 3 points. First, it uses multi-step training with contrastive learning and large memory bank. Second, augmentation strategy is used to precisely reproduce manipulated images. Third, it uses post-process methods that can enhance the embeddings by utilizing negative samples. For more details, please refer to this paper. For localization, we use a method called temporal network, which searches a path that maximizes the similarity between query and reference with the consideration of temporal consistency. We tune the parameter of temporal network using the training set of the challenge data. Next, I will introduce editing prediction. Editing prediction aims to predict the type of manipulations to determine which TTA to use in the later step. To train a prediction model, we first build a simulation dataset which contains nearly 15,000 generated samples using the training reference. We randomly select 2 videos and extract a random segment from one video and insert it into another one. To better simulate the challenge data, we also use the OGLI library to add manipulations, such as stack, rotate, blend. After creating the dataset, we train a model that uses frame-based prediction. We extract 10 frames for each video, and we consider it as a multi-label classification task. We fine-tune Covenant's model to predict. Here is part of our evaluation result. Since we apply TTA on stack manipulations, we check the result of vertical stack and horizontal stack, which all have very good performance. For TTA, we use multiple crops. We found that for stack manipulation, only part of the query can be matched to the reference. So we use 3 types of multiple crops to match both locally and globally. 3 types are 2 views for vertical or horizontal stack, 4 views for vertical and horizontal stack, and for the others, we all use 5 views. We extract descriptors for each view and concatenate them in the temporal direction with repeated timestamps. After the extraction of frame feature, we apply 2 types of post-processing. The first one is consistency weighting. The goal here is to increase the confidence score for copied videos. We found that the copied videos have more scene changes than non-copied videos, so the similarity, this part, between different scenes in copied videos is smaller than non-copied videos. So we propose this equation, where x is the original embedding of a video, and x prime is the processed one. N is the frame number, and D is the dimension. This equation naturally assigns larger weights to the copied videos than non-copied videos. Another post-processing is temporal concatenation. So far, we didn't use any temporal information, so we add this process to improve the temporal robustness. The process is simple. First, we concatenate adjacent frame descriptors and assign larger weights to the frames that is closer to the center. Then we use PCA to reduce dimensions. Finally, we apply the above 2 steps to all frames in a sliding window manner. Here we have an example that visualizes the effect of temporal concatenation on similarity matrix. This red box shows the ground truth of the copied segments. Compare the result before and after the temporal concat. We find the one after temporal concat has more obvious peak and also less noise outside the ground truth box. Next, I will show some experiment results. We first study ablations. We set our baseline here and study the effects of 3 tricks. We find multiple cop largely improves the AP of both tracks. Consistency weighting also largely improves the descriptor result and has some positive effect on matching results. Temporal concat also has some positive effect on descriptor result and has a little bit effect on matching result. Here is our final result. We achieved 3rd place for both descriptor chalk and matching chalk. Finally, I'm gonna talk about some things that we tried but didn't work well. The first one is to use the challenge dataset to fine-tune the ISC-DT1 model. A problem is we can't find a good solution to determine the positive pair and negative pair for video inputs. And we also find it difficult to create a validation data set that is independent of the training data set. The second one is to combine temporal information into descriptors. We find simple concat works better than some video alignment algorithms. We thought maybe the temporal movement isn't that important for video copy detection. So maybe copies are better detected by frame-to-frame comparison. The last one is how to deal with blending videos. We try to use UNet to decompose blending videos and reconstruct original images, but it failed. We also try to increase the ratio of blending data augmentation during the training, but it only has very limited effect. So these are some problems we might address in our future work. Finally, our conclusions. We presented a simple yet powerful pipeline for video copy detection. Our method incorporates several tricks such as TTA, consistency weighting, and temporal concatenation. Experiments show such tricks significantly improve detection performance. We achieved third place for both descriptor chalk and matching chalk of the VSC 2022. And that's all. Thank you for your attention.
We were muted, but thank you for your presentation. Right. Okay, are there any questions for our third place team?
Hi, I have questions. Easy. So, hi, Pei. The first question is that have you tuned the parameters of the temporal network, that is the TN? I found that tuning the parameters of the TN works a lot for the matching track. Have you tuned the parameters?
Yeah, we tuned the parameters of TN. Yeah.
Okay. So the second question is that in the matching track, I use 0.5 second for one feature. Do you use 1 second for one feature, or how long time do you use for one feature?
We used 2 PEFS, so that's 1 second, 1 second to feature.
Okay, that's the same with mine. So the third question is that I also try to solve the problem of the blending videos. It is very hard for my method. So do you have exercises to deal with the blending video or blending images?
Yeah, as I introduced, yeah, we tried the UNet, but it didn't work. So I think maybe it is kind of like a problem that cannot be solved. It's not mathematically, theoretically can be solved. Maybe we try to like search the papers about this blending videos, but there are just no related works. So I think maybe it's theoretically untackable.
Yes, thank you.
I have, so one of my favorite posters from CVPR a few years ago was this method. It's a double dip, like double deep image prior, and it tackles decomposing 2 overlaid images. And you can do it on like a video of like that's like a foggy, or sorry, it's an image method. You can do it on a video, like an image that has fog, and it'll decompose unsupervised into a fog overlay and then the original, unfogged image. And you can do like overlays and it can kind of decompose. It's unsupervised. Sometimes it works, sometimes it doesn't. It's very slow. It's an optimization based method, but it's really cool. And I've never had the occasion to use it, but I think about it often. It's a very neat demo.
That's
so-
awesome. Is that just for fog, or you can like decompose like random noises?
It's basically it's a UNet. It trains to reconstruct the image from two UNet models, and then a layer that mixes between them. And it's just easier to reconstruct if you have an image that is a composition of two distributions. It's just easier for it to draw if it learns like one of the images in one UNet and one on the other. So anyway, it's like a fun idea. It's not really practical. You know, I don't think it would be work within the time limits, but it's just a fun idea.
Oh, I see.
Okay, I think we're about at time. So I will once again thank all of our participants and thank you for the presentations. One more round of applause for everyone. All right, let me just get our text set up. Okay, our final keynote talk is Professor John Kalamos, who is a principal scientist at Adobe Research, where he leads their cross-modal representation learning work. He's also a full professor at the University of Surrey, where he co-directs the Decade Center on the Decentralized Creative Economy. Please welcome John Kalamos. It should be shared with audio. And let me just adjust this. Oh, one more thing. All right, hang on. I just have to find our Zoom view.
Yep.
Oh, I see. All right, we did it. Okay. Then. Okay, we can just make this small. All right, great. All right, Tim, let us know if we're not in frame. All right, here you go.
Okay, great. Okay, yeah. We good to go?
Yeah. You just. Sorry. All right, is that good? I'm just trying to get this bar to go away.
Okay.
All right, hang on. Sorry about this. One last try. There we go. Perfect.
Okay, great. Thanks for doing that. Okay, great. Well, good morning, everybody, and thanks, Ed, Jonius, and colleagues for organising this great workshop and challenge. It's been really exciting to see everything this morning. I'm going to talk today about content provenance and its applications to fighting fake news and misinformation, as well as other applications, which is the beyond bit in the title. And this is really a body of research we've been doing in the groups that I'm leading across the last few years, both in Adobe Research and also the University of Surrey. So, yeah, of course, fake news is a major societal problem and it's touching everything really, from our democracy to our healthcare to wartime propaganda, and it's also not a new problem. This is a photo of a proclamation dating back to the time of James II that took at the National Archives in the UK. And indeed, I'm sure this problem goes back even further as far as the spoken or word. Yeah, also the problem of visual fake news and misinformation is not a new problem either. This is a very well-known sort of classical example of a fake image of a girl interacting with some fairies at the end of the garden, but you know, sort of fooled people for decades before the photographer confessed that they were just cardboard cutouts. This is Elsie Wright back in 1917. But of course, fast forward to today, and clearly the problem's been amplified by technology. It's more the speed of communications than to blame than the manipulated media per se. You can see in half of these examples, there are fake images, manipulated images, but in the other half, they haven't used manipulated content at all. They're using real images here to tell news stories, fake stories, out of context. And of course, we saw many much more compelling examples this morning in conflict situations from Raquel and the talk from Witness. So, you know, this is an important observation then, that, you know, most manipulated imagery is not fake news. You know, clearly, if I thought that, I wouldn't be working, you know, somewhere like Adobe that makes Photoshop. But of course, not all fake news is manipulated either. There was a report, the TICS or It Didn't Happen report from Witness that was mentioned earlier, calls out that most visual fake news is actually unaltered images, just misattributed to tell a different story. So, you know, when you look at that intersection then between misinformation and manipulated images, it's quite small. And even trying to detect that is a bit of an arms race, you know, kind of antivirus virus situation as technology cycles. So this really leads us in my group, and also more broadly in the Content Authenticity Initiative at Adobe, to take a different view. Rather than deciding if an image is fake, what we want to do instead is try and inform the user more about the provenance of content. In other words, the origins of a piece of media. You know, how was it created, who created it, maybe what media it was created from. That's what we mean by provenance here. And if we can show the user that audit trail, that information, then they should be able to make more informed trust decisions about the content that they encounter. So in summary, instead of detection, we are about provenance. Okay, so, you know, this topic of provenance is really heating up now. It's a very timely topic. Last summer, of course, we saw the rise of generative AI. It's been around for a while, generative AI, but certainly through diffusion models, it's become a lot more capable. Models like DALL-E 2, Stable Diffusion. In recent weeks, Adobe also launched its own generative model, which is Firefly. These are models that you can write, you know, text prompts into, and they will generate a piece of artwork from scratch. And they can also perform other tasks like in-painting and out-painting and so on. And this has really propelled this issue of data provenance for AI into the mainstream. You know, what's the provenance of a synthetic image? Well, arguably it's the model, and the provenance of the model is, of course, its training data. And, you know, that's something that's become a major consideration for creatives, you know, as they question issues, things like training consent and the commercial acceptability of using these models. You know, it's rather predicated on the provenance of the data on which these models have been trained. And a central thesis really in this talk and our work really is that, you know, authenticity underpinned by provenance not only helps mitigate threats like fake news and misinformation, but also kind of opens up other applications layered on top, things like attribution of content, maybe even new kinds of market for creative content that could be created through better knowledge of content provenance. So I want to start really this body of work with a few photos from inside the National Archives in the UK. That book on the right records basically registered designs in the form of swatches of cloth over 200 years of design in that book. It's a record of design provenance. And my own interest in provenance really began in an academic project back in 2017 with the National Archives. Like many institutions, the National Archives are sort of grappling with the challenges of digital transformation. You know, no longer these sort of bits of parchment or cloth coming in, but now born digital images and videos. Even social tweets have relevance in our national record of government, and indeed it's the case in many countries. Yeah, actually in the archives also we find a possible, hopefully accessible explanation to another technology that underpins quite a lot of our work, which is blockchain. Maybe a quick way to explain blockchain by way of introduction in this talk is using the archives. Specifically, there's something the archives store, which are these rolls here called the rolls of chancery. These are medieval court records that are sort of stitched together into a patchwork of cloth, making the roll. And even today, the second highest judge in the land in the UK is called the Master of the Rolls. He looks after the rolls. And the motivation for stitching together the pages of these court records is, of course, that no one could remove a page of records because it would leave a big hole in the parchment. And this is sort of a little bit of an analog version of what blockchain is today in the digital world, with the hashes that bind data together. So yeah, this project I mentioned then that we worked on with the National Archives, we called it Archangel, and it used blockchain to tamper-proof records in the National Archives. And the idea is that when a document comes into the archive, it's fingerprinted using an AI algorithm, and that fingerprint is then stored in the blockchain, which is this sort of immutable append-only data store. And yeah, then the idea then is later when the document is released by the archive, it might sit on that record for some time. Then the public can fingerprint it again and check if that fingerprint kind of matches the one in the blockchain to check it hasn't been tampered with. And we deployed this Archangel project across the National Archives of several countries. I don't know how good everyone is on their flags, but you can see here, obviously the UK led the project. The US, Australia, National Archives, Norway, and Estonia all participated. And the idea is that the archives mutually underwrote the integrity of one another via the blockchain, so that there's a kind of technological basis for trust. And this is important because it's sort of substituting institutional trust me because I'm the archives, or a government body, which institutional trust is kind of being eroded at the moment in public life, with a technological underscoring of trust. And this was really the experiment in this trial. And Archangel, yeah, was the first to really do this for digital preservation using a blockchain. Yeah, in terms of the fingerprinting technology, well, Archangel used the deep learning model to create that fingerprint. One of the properties of that fingerprint is that even if the image changes just a little bit in some sort of benign or non-editorial way, that we would still end up with the same hash. And obviously this would allow for things like changes in quality resolution. Particularly in Archangel, we looked at video, which gets transcoded over time. One of the curatorial duties of the archivist is to make sure that information is always accessible and viewable, and transcoding video is a common operation. And when they do it in bulk, it can mess up due to maybe the video not being fully conformant, things like this. So yeah, the idea, of course, is that we need to use a content-aware hash to do this, because a standard cryptographic hash like SHA would break if even a bit of the content changed. So the idea is then that the AI fingerprinting allows the matching across different renditions, and this brings us then into the use of fingerprinting to match content that is distributed online, which suffers from the same problem, right? If you post an image on social media, then it will be transcoded in different forms, what we call renditions, and we want to be able to match those using a visual copy detection, which of course is the topic of this workshop. So yeah, this challenge of authenticating content online is something we've been addressing in my group in close collaboration with the Adobe-led Content Authenticity Initiative, the CAI, which now has over 1,500 partners, which is really exciting to see that level of traction. And CAI is tackling misinformation through provenance as a content attribution problem. And so we're not trying to automatically kind of detect and judge or flag fake content, but as I say, trying to make users more informed about the origins of content so they can be enabled in making trust decisions. And well, provenance for authenticity is perhaps arguably one of the most important downstream applications of content provenance. We'll talk more about that today. But thinking a little bit further beyond that application, what else could content authenticity underpinned by provenance achieve? Well, what if in a few years people are not going to buy or use media without some sort of guarantee about its provenance? We're already seeing the emergence of that attitude in generative art, right? People don't want to use perhaps a piece of generative art unless they can be assured of its provenance, that it's commercially safe. And there are also emerging markets that are underpinned by provenance. There's non-fungible tokens, NFTs, are basically tokenized forms of artwork that are traded on the blockchain. This got, I guess, popularized a lot during the pandemic when traditional routes for creatives to market their content were closed down. You saw a real boost in the use of NFTs to trade artwork. But really, this is a platform that is trading this work underpinned by the ownership provenance of that artwork, and it's still used extensively for digital collectibles. It's not perfect. We'll talk maybe later about how that we can try and address some of its deficiencies, but it shows the value of provenance already in existing emerging decentralized markets, and in future markets as well. Platforms that create value through digital exchange of digital assets, like metaverse platforms, would probably be underpinned also by strong guarantees of provenance and ownership of content. So, thinking even further then into the future, perhaps an even more exciting direction would be thinking about how this changes the creative practice, right? So, imagine a future in which content provenance enables us, to determine the attribution, the authenticity, the rights, even the pricing of content in a world where any user could generate content and put it on the market. I mean, imagine you're a consumer here taking a video of a gig, and maybe you put it on the market and some broadcaster picks it up and they want to use it. And they may be able to do that and compensate you through some micropayment mechanism mediated through strong knowledge of provenance and ownership of that content. How is that going to change the way content is produced, the content is marketed, maybe even the way that value is created in our emerging creative economy? I think it's all underpinned by strong provenance technologies. So much of the work that I present today links with an emerging open standard for provenance that we at Adobe are contributing to, along with many others in the industry, called the C2PA, which is the Coalition for Content Provenance and Authenticity. C2PA encodes provenance information in the metadata of assets. Basically, it's a metadata standard, and the packets, the record of this provenance is called a manifest in the C2PA. It's cryptographically signed. It's made up of what are called claims, which contain facts, assertions about the provenance of an asset. So, for example, who made it, where was it captured, what kind of operations were performed to create that asset. And that could link back to other ingredient manifest assets as well. So these manifests link together in a graph, create a provenance graph, and they're all bound together by hashes of the previous manifest and hashes to the pixels, the digital content in the image. In what we call a hard binding, which is just a kind of a SHA hash, or there are several kinds of cryptographic hashes supported. So this is great that lots of products are emerging that speak C2PA. Photoshop and Lightroom and Firefly, our generative model at Adobe, included. But there is a challenge as well, and the challenge is, of course, that metadata is trivially stripped from assets as they're shared online. All social media platforms strip this metadata, among other metadata, and of course attackers could strip the metadata as well and even substitute the metadata to tell an alternative provenance story of an image. So I mean, this is a big problem, because this is an attack surface that could deprive an image of its provenance information. It could be a method for misattributing content. And so one of the solutions that we put forward then through our work is to use content fingerprinting, this idea of creating robust perceptual hashes in order to fight this threat. And when products like Adobe and other products create a manifest and store it inside the image, what we can do is take a copy of that manifest on an opt-in basis, of course, and store that in Adobe's cloud and key it off this robust visual fingerprint, so that if we see an asset circulating in the wild without this metadata, we can recover its provenance through lookup and present the user with that information, that trusted record of provenance. So the flow kind of looks a little bit like this for a creator. When an asset's created, it is basically sent up to a signing service, which cryptographically signs and seals that manifest. And then at the same time, we take a fingerprint of that content and store it in this effectively key value store. So the key is the fingerprint and the value is the manifest. And then the asset goes on its way out into the world. Then later on, a consumer encounters that asset, say on social media, where its metadata has been stripped off. So it has no manifest now. It may have gone through some sort of non-editorial transformation, some rendition, maybe some degradation in quality, format, resolution change, and so on. And then basically the user is going to compute a fingerprint. Again, we're going to basically use that short binary hash to look up in some scalable index the manifest, and then the user gets a copy of that manifest in the same way as if they may have found a manifest in there originally, would be visualized. So this system's already hard at work in production, storing millions of manifests from some of the products I mentioned. Adobe's recent generative model, Firefly, also does this automatically. So we call this feature in production content credentials. And you can see bottom right that there's a website as well. It's a Verify website where you can drag and drop images into the website to view these content credentials. And if the credentials don't exist, then in the metadata, then you can go search for them using the mechanism I just outlined. And this is great because we can do things like show whether an image has been created by the generative model, regardless of where it turns up. If I have a look at this snapshot of a TV containing such a generated image, we just a small manipulation, crop the image, drop it into Firefly. Into Verify, and we can see that it's a Firefly image, and we can restore that provenance trail. So I'm going to talk now a little bit more about how these fingerprinting models work. These are covered in various papers over the last few years from the group, spanning images, video, and looking not just at matches, but also visual change summarization and adversarial defense as well. The first I'll look at is the fingerprinting model. There's actually two technologies in this flow. First is the content fingerprinting to do the robust matching that I've been describing. And then we also have a technology we call image comparator network, ICN, which visualizes any manipulation between the query image and the original in the database. So first of all, just some results. So this is some examples of the matches that the model is able to make over a corpus of 150 million images, in this case from the Behance platform, which is a large artistic portfolio site that's run by Adobe. And we can see here that on the left is the query, and then the right is the top one result. So it can deal with quite a lot of quite severe augmentations. And the method itself is an object-centric approach. So by object-centric, I mean we're computing some visual fingerprints of salient objects in the scene, as well as the background, and encoding those into a scene graph, where the nodes are carrying this visual information and the edges are carrying spatial relationships of the objects, their relative positions and so on. I'm happy to take questions on the detail offline, but we developed a kind of transformer-based approach that's contrastively trained to be sensitive both to large and more subtle manipulations in the scene, but robust to these non-editorial changes, these benign transformations that occur as content is renditioned online. And some of the data that we trained on in the paper, although we don't do this for production, but in the paper we benchmark on this PS Battles data set, where there's a nice paired set of data where we have original and manipulated data that we can train and evaluate on. And we started out evaluating some of the sort of classic perceptual hashing approaches, the p hashes and things like this, and quickly realized, as many others have done, that contemporary deep learning approaches tend to outperform these quite significantly. And in fact, even using contrasted training of fairly regular backbones, we do pretty well, just on this data. But object-centric methods outperform these on benchmarks. We had a benchmark related to matching non-editorially transformed, benign transformed images, and another looking at how we could match on these manipulated images. So one of the curious things about deep learning methods is, of course, that often small imperceptible changes can be made to an image in order to drastically change the prediction of a deep learning model. We've seen this in classification, and a couple of years ago, I think it was Meta maybe showed in one of the workshops at CVPR that this applied also to search and hashing models as well. So we did a little bit of work exploring the adversarial defense of these image fingerprinting models, because we need to consider the very real possibility that an attacker can introduce an adversarial attack to an image that's kind of imperceptible, but can survive through these benign non-editorial changes in order to force a lookup of a different asset in response to the query. So yeah, again, I can take details on the specifics of the adversarial training that we did, but it's in a paper that we published in the CVPR workshop in media forensics last year. In terms of the image comparison model, we have this pairwise comparison network that basically runs over the retrieved results in order to produce a heat map that highlights the manipulations in the image, but ignores any changes due to these non-editorial rendition-based transformations. It's trained using a sort of augmented data set with a bunch of the kinds of transformations that we saw highlighted in some of the winners of the competitions here in the workshop talk, things like the Augley and so on. Yeah, the network does a little bit of alignment using a RAF-based estimator for flow fields, and then does this pairwise comparison. And one of the contributions of the paper introducing this was some annotation to show where the manipulations are in the PS Battles data set, actually. And yeah, just some examples of some results here. In the green, we see the ground truth area, and in the blue, the detected heat map, and you can see the predictions very close, even for the kind of out of place warping operations. And as another output of the model, we also have a prediction that gives us the likelihood that the image and query pair are the same, which can be used to re-rank the results. And this is important because, you know, it's quite hard to do a web scale kind of look up with a model and come up with a highly accurate kind of top 100 shortlist. So we then go through to this pairwise re-ranking to improve the score. And then we leverage also that pairwise score in order to come up with a decision on where we can cut off, you know, hits and misses. Because it's very hard to do that accurately by thresholding on a metric embedding at web scale. So yeah, that's why we have this pairwise comparison step. So I have a short video now that shows you some of this in action. I will play it.
Online misinformation and fake news are serious societal challenges that Adobe is proud to be addressing through the Content Authenticity Initiative. How often do we all scroll through our Twitter, come across a photo, like here, of the president, and we ask ourselves, how can we tell if this image is genuine? Content fingerprinting lets me quickly check the image against a database of authentic content stored securely by content creators in Adobe's cloud. I drag the image in, and the content fingerprinting tool shows me that the image is a partial match. It has been manipulated, and the manipulated area is highlighted. And now I can make a better decision on whether to trust the content. How about this image of Russell Brown? We see that it matches exactly to an image in the database. There's no manipulation. But now I'm going to edit that image in Photoshop, and I'm going to switch the wand out for an ice cream. So I'm making my own fake news here about Russell and the ice cream. I'm going to save it, and then I'm going to drag the image into the content fingerprinting tool. The system has made a partial match. Again, it's highlighted the manipulated area. Now I can make a better decision on whether I can trust this content. So as content gets shared around, it can also experience benign or non-editorial changes to the content, like format or resolution change, or here, quite severe noise and degradation. Content fingerprinting uses Sensei's advanced AI to match the images even if they change format, resolution, or here, exhibit quite severe degradation. The fingerprinting technology highlights only the editorial change, the glasses, and ignores the visual artifacts from the noise and non-editorial changes.
I'll stop the demo there. So we've also explored the problem of fingerprinting video, very relevant to this workshop, I think, you know, particularly for partial temporal or fragment matching for video. And here, initially, we took a very sort of, I guess, simplistic approach, applying contrastive learning to audio spectrograms and also visual features that were separately encoded. And in this paper, we kind of explored early versus late fusion approaches to dealing with the fusion of those modalities. And then we create, I guess, like a lot of the kind of classical large scale lookup stuff, we create an inverse index to match video chunks over which these descriptors have been computed in order to come up with a short list of matched video. This worked reasonably well, but doesn't really scale because of the chunking. So we introduced recently an improvement on top of that, this video alignment and differencing approach. And there were several contributions, one of which was taking an adaptive chunking strategy to basically just build that index a lot more efficiently. But then, we then layered on top of that some fine scale temporal alignment. So the chunking gives you a kind of coarse scale localization of your partial fragments, your query into the larger original video. Then we, within that, make a finer scale, a finer grain alignment using a transformer-based method to do the alignment. And then having aligned the videos, usually, fairly spot on, within 1 or 2 frames, we get a good alignment. But then we want a difference between the two of them to highlight the area of manipulation. And we have a kind of space-time version of that image comparison network to do that. So it needs to be space-time to mitigate any very minor misalignments that remain in the from the fine scale alignment.
Here in the demo platform, we have in the left column the option to select a video query, which in this case is this video with plane flying in the background. Second column is where we retrieve the original using the retrieval module. We use the alignment module to align the retrieved video and the query. Finally, we use the differencing module to outline the edited part of the video, and we superimpose that on both of the videos. Second is in painting. The person was removed from the video. So again, we use the query to obtain the original using a retrieval model, and as we can see, there is indeed a person walking on the street. Then we use the alignment to align both of them together, and in this case the alignment is very precise. As we can see, both videos go together frame by frame. Finally, we use the differencing module to obtain the outline of the person. And finally, an example of a swap manipulation where the query video is quite homogeneous, and because of that, the retrieved result, which is almost 4 minutes long, is not aligned perfectly with the query. It is aligned quite close, but there is a couple of frames discrepancy, as you might be able to see in the column number 2 here. We chose this example to show that even in the cases where the alignment is not matching the videos exactly correctly, the differencing module is still able to ignore the differences in the faces here, for example, and focus on the object that was manipulated.
Okay. So so far we've discussed fingerprinting as the main recovery route for metadata stripping. But of course, watermarking has been explored for many years, and including for embedding of content ID inside images and video. So where does watermarking fit in? Well, watermarks can of course also be stripped. Any mark can be, in our use case, stripped away by an attacker. And actually, when you think about it, it's kind of desirable to strip it or have the facility to strip it, because if I've got a couple of image assets with watermarks in them and I want to combine them to create a compound asset, a new asset, then I would want to put a fresh watermark inside that asset. So strippability of watermarks is something that we have to, acknowledge and live with. That sort of influences then where they, I suppose, sit in terms of the attack surface of this stripping problem, which I've tried to summarize in this table here. If you look at these first 2 rows, which are like watermarking and metadata, they're pretty similar. They're just sort of different channels, if you like, to bear a form of metadata, be it the full manifest or the ID. But the fingerprinting is quite complementary, which is why I guess we've explored the metadata and fingerprinting initially. But watermarking, I guess, does carry with it an advantage in the sense that even though it's strippable by a determined adversary, it isn't, if you have a robust one, routinely stripped by online distribution platforms like social platforms. So there is a sort of a convenience there. If you had this watermark inside an image, you could then identify whether it's worth doing a network lookup if there was metadata absence in it. And that's an area we're pursuing at the moment. We had a paper here in the workshop yesterday, media forensics, on a robust watermarking technique that is robust to these kinds of benign transformations online, and imperceptibly stores roughly the same capacity ID as a manifest ID, a GUID, for this metadata standard, the CVPR. So here's one use case for that. It's kind of prototype web extension we built a while ago called Trust Trace. And the idea is that you can see some images within the web page are being searched with a fingerprint or a watermark, it doesn't matter which, as they're viewed, and then a lookup performed in order to surface the provenance information from one of these cloud manifest stores. Actually, one of the interesting things about this prototype is it didn't just use these markers embedded in the image. It also the database was actually on a blockchain. So instead of having a centralized point of lookup, we had a decentralized database, which had kind of open governance model. And in this work, which is another very recent work, we were using blockchain again to create a sharded decentralized database for basically doing this fingerprinting lookup of manifests. This particular use case, we were using a recent feature in the C2PA standard to indicate consent for generative AI training. So we call this like a decentralized do not train registry. And the idea here is that an image could be checked against this decentralized database for training opt-out for AI training. Yeah, one of the nice things about blockchain then is that there's no sort of centralized authority for managing or controlling this database. So yeah, so kind of moving then towards these ideas of alternative uses for provenance then, we come to this idea of using provenance to underpin content trading and decentralized markets for content. I mentioned NFTs earlier. An NFT is a unique and indivisible kind of digital asset, like a trading card or a piece of digital artwork. You know, in physical artwork, value is often, you know, created through provenance. This is on the right-hand side a snapshot of something called a catalogue raisonné, which is a sort of authoritative centralized ledger used to track who's owned which physical artworks, based in the Louvre in Paris. And there's this provenance trail that gives, you know, a copy of the Mona Lisa no value, but the real Mona Lisa value, you know, even if they were pixel identical, it's the ownership provenance that is at least partially responsible for the value of physical artwork. So NFT is really like a digital version of this. You know, with NFT, the value is derived from an asset's provenance, and that's tracked immutably within the distributed ledger. What does that ledger look like? Well, this is a sort of a diagram of that. It's really just a mapping, like URL of an asset to a wallet address, which is a bit like an identity on a blockchain. The URL points at some metadata, which in turn points at the asset, which is usually stored in a distributed file store like IPFS. And this mapping is stored in something called a smart contract, which is a bit like an object in an object-oriented sense that lives on the blockchain. So it has state. In this case, it has a key value store mapping URLs to these addresses. There are some big problems with this model of a decentralized market with NFTs. You know, when you buy an NFT, one of the biggest problems is that there's no rights framework that goes with it. You know, if you buy an NFT, if I buy an animated character online, how do I know I can use it in my game? I don't. It's absolutely, you know, gray area. So this kind of really limits the utility of NFTs for creative reuse. You know, this is often why they're used really as either collectibles or just as tools for digital speculation online. But perhaps if there was a rights framework, they wouldn't be. They would be more useful for creative asset reuse. Another big problem is copy minting, which is where people just copy paste content and remint it, which basically means put it on the market as an NFT. And that's where, again, provenance can help mitigate, you know, that threat. There are, of course, other concerns as well, things like the energy footprint. These actually are largely mitigated, I would say, now with proof of stake networks, but certainly many existing weaknesses. And at least with C2PA, we have, you know, kind of a way of mitigating this copy minting threat, because if you think about it, NFT is providing only ownership provenance, who owns or owned an NFT, but C2PA provides the creation provenance, like how is an asset made, by whom, and so on. So if you combine these two by signing your NFT images with C2PA metadata before you mint them, then you can say something about the origins of an image you find on a market and mitigate this copy minting threat. And indeed, several major markets have started to do this with the C2PA metadata, which is very exciting. A final piece of work I'll talk about today is really how we've extended NFT further to incorporate rights and attribution to address some of those other deficiencies I mentioned. We call this extended NFT framework the Aura Triangle, which stands for ownership, rights, and attribution. And this is a poster we also had at the Media Forensics Workshop yesterday. This diagram kind of shows at the top traditional NFTs. That's the diagram I just showed you a moment ago. But what we've done here is extend this so that every creator operates something called a rights contract, which is another form of NFT. That contract for that creator owns their NFTs, but then it can dispense rights tokens to individuals for various different rights, including, for example, the right to train an AI model. And then with those rights tokens, you can actually issue micropayments, royalty payments back to that creator in order to create this kind of decentralized market for creative reuse. So we're really excited about this framework. It is just a prototype framework at the moment. But we believe this framework could perhaps underpin, this sort of a new model for the decentralized creative economy and digital work in the future. So talk a little bit more about the system we presented then yesterday, which we call Aquila. It's really an end-to-end framework for recognizing and rewarding creatives for the reuse of their work, creating this decentralized market for content rights. I mean, in the paper, we focus on this kind of timely problem of generative AI and the rights to train and reuse work for generative AI training. And as I say, it exploits this aura triangle to do that. It kind of combines that with a robust visual attribution method, which is actually based on the fingerprinting technology I introduced earlier in the talk. So first off, let's look at how C2PA can be used to enable synthetic media provenance. So the synthetic image at the top here, this is obviously just a toy example with MNIST. There's the synthetic image. It has a manifest, and the manifest has one ingredient, which is the model that created it. And the model itself also has a manifest. That anything can have a manifest. This binary blob can have a manifest, and that contains ingredients. But in this case, there are multiple ingredients, which are the training data that we use to create the model. And then inside that manifest, there's a possibility to link across to the NFT ecosystem, and then in which can be defined the ownership of those assets. And this would allow us then to make micropayments to the owners of those training images. I can show an example of this. This is an example of a dream booth. What is it? A dream booth synthesis of a cat. So the cat is sitting on the beach, but it's not just any old cat. It is a cat that has been, obtained from a handful of concept images. So Dream Booth lets you sort of personalize or fine tune a generic diffusion model to create specific content. So what we can see here is exactly the framework I just had on the previous slide. We've dropped the synthetic image into Verify, and we can see here that the cat has been generated by a Dream Booth model, which in turn has been derived from a Stable Diffusion model, but also has been fine-tuned from a bunch of concept images. And then we know then that this image has provenance to these concept images, and we could choose to potentially reward the originators of those images. Of course, this only works for either very small toy data sets like MNIST or small handfuls of concept images like with Dream Booth. If we're talking about diffusion models with millions or billions of images, it doesn't really work because you can't divide a payment a billion ways. So what do we need to do? Well, we need to identify what subset of training data is relevant for a given training image. And I want to refer back to that project I showed you right at the beginning with the National Archives, and that book that had all those registered designs in it. If you recall, was a set of material swatches part of the UK's registered design catalogue. And we were exploring in that project design provenance and whether the provenance of design motifs like Paisley's and so on could be traced over time using our image fingerprinting technology in like a patchified form. And it was pretty successful. And we started to think, well, actually is piecewise regurgitation of images a good way to measure attribution for generative AI? And we applied it in that way for synthetic media provenance. And it turns out that it can, and it answers it reasonably well. So this slide here shows some diffusion generated images on the left, and patches of those images for illustration here have been attributed directly to the training data of that diffusion model, which in this case was some Adobe stock images that were used to train that model. So the number here is showing an aggregated score of the patches that have been matched using the fingerprinting between that synthetic image on the left and those millions of training images in the training set. And this attribution score can then be used to pay a royalty by that Aura framework back to the owners of those images. You know, as well as enable those creators to opt in or out of their data being used in the first place. You know, here's some more examples. This, you know, you can see attribution here, kind of roughly even attribution in this case. This is an example of stable diffusion using Lion, and you can see that the Aquila framework made an even attribution because the images in this case look like maybe they've been potentially taken from a product catalog or something, have been you know, largely memorized and have strong resemblance to that generated image. So the fingerprinting model is working well for attribution and credit apportionment, which, you know, clearly is another use case for provenance. Yeah, some more examples here. This is style apportionment as well. And here's a video of it all working together in this Aquila prototype to pay an AI, a Gen AI contributor.
Project Aquila enables creatives to define rights to their content and to receive recognition and reward when those rights are exercised. Here we're purchasing images of a specific fish from Adobe stock. We're using the Verify web app to view the CAI content credentials that are shipped inside every stock image. This metadata, called a manifest, describes the provenance of each image, which creative made it, and how. Dreambooth is a gentech that can specialize generic diffusion models, like Stable Diffusion, to create images of a specific object like this fish in a swimming pool. Here we've modified Dreambooth training to create content credentials that describe the model and its ingredients, which are those fish concept images, which in turn have their own provenance, as we saw. When we drop that synthetic image into Verify, we can see its end-to-end provenance embedded using the content credentials metadata. The synthetic image shipped with the manifest inside, describing the model it came from, which in turn links back to those concept image ingredients, so recognizing the creatives that made the image. As a consumer, let's say that I come across that synthetic image of the fish in the swimming pool online, and I want to reward the creatives that made it happen, who contributed those concept images of the fish. Some of those concept images are NFTs owned by their creators. The Aquila framework enabled those creators to assign training rights for those images, and also enables those creatives to receive donations and royalties for their use in Gentech. In this demo, the micropayments to those creators are being made in a cryptocurrency. Here we're showing the creator's wallet is empty, and using only the JPEG file of that synthetic image, I'm going to use this command line tool to send a donation to those contributors. The tool uses the content credentials metadata present to trace back to the concept images. 10 of them are registered as NFTs, and the cryptocurrency is distributed to the current owners of those NFTs. We can see here the transactions completed, and now the creator can withdraw their funds to their own cryptocurrency wallet, receiving the reward for their contribution to that image.
Okay, so in summary, I've shown, I guess, a kind of layered stack, starting with methods for determining image provenance, which then enable authenticity, which in turn drive market value and create opportunities to create kind of decentralized trading floors for content, including for Gen AI compensation in this prototype. So in other words, strong provenance tools provide a foundation for content authenticity and beyond. And we've described various technologies to establish this provenance, C2PA standard, steps to cover the attack surface of metadata stripping, such as fingerprinting and watermarking, and visual attribution methods for synthetic media. And yeah, it's interesting as well to see the role of decentralized databases and tokenized trading, which combines with these to create this kind of new emerging markets for creative content. I guess we don't know, of course, what the decentralized creative economy will look like in the future. It may look very different to this, but I think regardless of the shape of it, it will very likely be underpinned by tools for strong content provenance. So I'll leave it there, and with some references as well. So thanks very much, and thanks to the contributors as well. Yeah. Yeah, happy to take any questions.
I have a very basic one.
Yep.
So on the provenance of synthetic images that you were showing, are you able to do that with all diffusion models or only with Stability AI because they sign up to CVPR?
Right. So the question is, would the synthetic media provenance work with any diffusion model, any Gen AI? It would, provided the the Gen AI service was signing these manifests into the images, because the provenance of the image here is, we're not detecting which model made an image. We're just relying literally on the metadata to say which model made the image and therefore what training data made the model. Of course, there are technologies to try and identify which model made an image. We've looked at that problem as well. And I think there are even some startups now looking in that space. I think maybe with some screenshots of some of those in your talk, Echo. So yeah, but it would work in any generative model that chose to adopt the CTPA standard. Yeah.
I have a question regarding the visual fingerprint for you.
Yeah.
So, I think we have the case of the small edit that results in a copy.
Yeah.
And that's an example of a positive example of a copy.
Yeah.
And we have also the case of a hard negative where you're actually doing different images, but many things are similar. So let's say an example of an image that was taken just a few seconds later, or like slightly different viewpoint. The other thing that is that a model that predicts a copy in the first case of a small edit and not a copy in the second case of this hard negative example. So what's your view about this very difficult problem? Is it worth focusing on that, or maybe it's not worth that much because these are difficult cases that come from the same user?
Okay, I'll try and summarize your question. I think your question is about whether we would admit partial matches or whether we should focus on partial instance matching as a facet of the content fingerprinting problem for images. Is that a reasonable summary? I mean, I think it definitely depends on the use case. For the use case that I've outlined, which is manifest recovery, we actually don't want to match partial images, right? We want to, if there's an image circulating online that's had its metadata stripped, we literally just want to reunite it with its metadata. So it's interesting because the papers that we did publish in 2021, 2022 on the image fingerprinting, which kind of formed the basis for what we then went forward to use, we're quite good at partial image matching, but actually in production we don't want to do partial image matching. So yeah, that was something we had to change. Yeah.
I saw also it might be some of continuous from the previous question. You demonstrate in some cases where foreign objects are spliced into the either images or videos. And I'm curious, if you introduce some more clutter inside the media, is there a point where this kind of system starts to break, not performing at all? Is that, I mean, is the amount of clutter, is the strength of the manipulations? Do you have any view on this?
Yeah.
Until what point are they working?
So I think it is a similar question, Georges, because I think it relates to, how do you define a partial image match? And as I say, in our use cases, any significant change we don't want to match under, because we don't want to that would be a different image, right? So yes, but I mean, in the paper, particularly that Oskanet paper that I highlighted, the scene graph based approach, yeah, we were quite robust to partial insertion of objects, but obviously the more you include the original image with additional objects, the less it will match, right? I mean, so you would just need to draw your own task specific threshold in that case. Yeah. Another question, yeah.
You mentioned some work on attacking fingerprinting. So under what assumptions does these attacks are successful? So what does the attacker know about the fingerprinting method, or what kind of access do they have?
So the question is the work on adversarial defense, yeah, what assumptions were made? So in that paper, we were exploring the kinds of attacks, and I forget the specific name of the paper, but there's a paper, I think, in the workshop on media forensics, CVPR 2021, where they were exploring these kind of L-infinity norm perturbations on the pixels, so LGSM kind of methods to perturb an image so that it hashed to the wrong lookup for an image. So we were looking to mitigate that particular threat. But then we adapted. So at the time of that paper, there weren't many approaches to adversarially attack caching and search models. So that was the main one we focused on, but we did try and adapt some other common methods for classification models as well. And in the paper, we we looked at training under LGSM type perturbations for the adversarial training, but we did then try and evaluate its susceptibility to attacks from these other models, these unseen models. And it generalized relatively well, actually, the protection. But of course, you know, if you have a white box scenario where your model is in the wild, I suspect it would be possible to optimize, you know, against that model. Yeah, to attack it. Yeah. Okay. Well, if there are no further questions, thanks for your attention. Yeah.
All right, well, that's the end of our workshop. Thank you everyone for attending. Thanks once again to both of our keynote speakers and to all the participants in the challenge.
Thank you, everyone. I'm stopping the recording here.
Thank you.
All right.